All right, I'm going to start. Welcome to the IDEAS Annual Symposium. Each year we come together to celebrate our accomplishments and look ahead to another exciting year of research and education. Please welcome our Institute Director, Alex Szalay.
Thank you. So I thought this has been a year when a lot has been happening in the outside world. So we are living through a revolution of an unprecedented pace and agility. And so I thought that really in the next few minutes, I would just really like to talk about, what is the trajectory? We have to change pace, and we have to change trajectory and directions. And so I would like to talk a little bit about what I think we should be doing in the next few years. So what's ahead of us? And the big challenge here is the tension between agility and tenacity, and how can we compete in this world, and who are we competing with? So we see that in industry is moving at an extremely agile pace. So basically half of the papers written in AI are obsolete in 6 months. How can we teach a semester course when we know that half of the material that we are teaching thinking of at the beginning of the semester will be either wrong or outdated by the end of the semester? And how can we repeat this then every year? Basically, we have to write a new course. So how can we compete with the billions of dollars that are spent on these data centers and the hundreds of thousands and soon millions of GPUs deployed? We can't, simply. And our faculty hires are for 40 years. And even though these people are who we hire today as assistant professor into AI probably will be able to change the course of research direction, but they won't be able to change it kind of very rapidly. It will take a few years until they adopt. So how can we adopt in this new world? There is one area we can actually compete. And especially important to look at the Nobel Prizes 2 years ago, where both the physics and chemistry Nobel Prizes went to AI. And the chemistry Nobel Prize went to Google DeepMind for AlphaFold. And that was an amazing discovery, an amazing piece of research. But we should not forget that also it was based on a data set on the ProteinDB that cost $20 billion to build and about 20 years. And Google would never have had the patience to create such a data set on its own and on its own expense. Plus, the 20 years, Google has been a very different company 20 years ago. So that's not what they do. But this is what academia does. So the ability to create actually large, unique, game-changing data sets is something that would be the safe space that academia can actually operate. And, our history is tied with this. The only issue is that academia and universities can't afford $20 billion either for 20 years to build a data set. Although, we have been part of the Sloan survey, which started 25 years ago, and we are still working on and producing newer versions. But the lesson there is that we have to learn to create these data sets in a much cheaper and much more scalable way. To use actually some of the techniques coming from industry to learn about their experience and scalability. And this, in many ways, the Sloan Sky Survey was the first astronomy project that was built on the principle of scalability, where we fill the focal plane with a mosaic of CCDs. Our computing was based from the very beginning on verbal clusters and so on. So this may be the safe space, but again, this doesn't mean that we can lay back and sit idle. So this still means that we have to increase our agility dramatically. And what we see is actually through funding coming, for example, from private foundations, there are many mid-scale projects emerging at universities which are in between the $1 billion experiments like LSST Rubin and the $300,000 grants. And typically these experiments are much more agile, and they want to get results much more quickly and much cheaper than previously. And what we can already see that these are adopting AI actually at the workbench. So what we will see, my prediction is that we'll see that interactive uses of AI will optimize experiments. They basically use many, many parallel sensors, and we will have to convert this almost immediately to tensors, so AI-ready data. And when we look back, many breakthroughs in science over the last 20 years came out from unique new data sets like the Human Genome Project, which released the data in the open, the SDSS or the COVID data that was important that it was open from day one, or ImageNet, actually in AI, but it was always also combined with disruptive ideas, which meant that clever people were able to access the data freely. The scientific data analysis is also evolving. I used to go down to Virgin and just buy a Miles Davis LP and took it home and played it on my record player. You can ask, what has this anything to do with AI and data? But bear with me for a minute. Because, these changes in the music industry, which then went to iTunes, where the publishers, the people who run the music business hated it, didn't like it, yet it happened. So these disruptions happened. So the next stage was iTunes, where I didn't have to buy the whole record. I could buy actually one song at the time and download it and play it on my MP3 player. And today we are in a world where everything happens online, in Spotify and Pandora, and I get a stream of the music. How does this relate to data? We used to take the tapes and then the disk drives from the mountain and bring it home and analyze on our own computers. And I was writing sequential C code where it was iterating through the data line by line using my own code. Then came basically the SQL databases that we built for Sloan, like the Sciserver and the Sciserver. And here we can actually store the whole corpus of data from a survey in a database, but I can access it one song at a time by writing a SQL query, which gives me just enough data to write the next paper. And here I don't have to write an iterator over the data. I basically issue a declarative query. So I tell it what data do I need, but I don't tell the system how do I access it and how do I extract it. It is smarter, it can figure it better itself. And basically, in Spotify and Pandora, I don't exactly tell the system which songs do I want. I give kind of my intent, what kind of music I want to listen to. And this is where we are heading today, that essentially we can give some prompts instead of writing the SQL query, and the system will actually then perform the data extraction and the data exploration for us instead of writing, very mundane 2-3 line or 5-line Python codes to do an XY plot. So, but the important thing is that in order to get to this point, which is already there at Google Colab, and Hugging Face enables us to basically run pre-existing models, except that on data sets which are Mickey Mouse compared to real life. So, and then this is what we are trying to do with the Sciserver on a limited scope, but on much bigger data sets. But basically, this means that we will have to rewrite sooner or later most of the software that exists in science. And this is a big challenge, and many of you are part of that community. So this is, Gerard will talk more about the Sciserver, but basically here, these are all the projects on the Sciserver today. It involves actually, at this point, many petabytes of interactive access to all this data, and provides a framework where we can run Jupyter and actually PyTorch and TensorFlow on top of these data sets in an interactive fashion. So starting with Sloan, we had the ability, looking back the last 25 years, starting in 2001, we built the Sciserver, and since then, it is still going. So we are now at 6.3 billion web hits, 1.1 billion SQL queries that were typed in, over 10 million distinct IP addresses for the users, and it generated 15,000 papers and 770,000 citations in a community that is much, much smaller, for example, to bioinformatics or medicine. Then in 2006, we started to build a turbulence database where we can place virtual sensors into large simulations of turbulence. And today, and deliver basically this virtual sensor send the data stream back to the users. So you don't have to download the data. You can select where you want to look and place your sensors there, and then you get calibrated data back there. Today, we are 600 trillion points that we deliver to the world. The data set is used by NVIDIA, and the turbulence data was also selected by NER, the NSF-led AI initiative, to be placed as a tiny bit of our data actually into Hugging Face. But we were one of the 10 data sets that we selected for this. Recently, we started AstroPath with Jenny Staub, where we are shooting for 1,000-fold increase in collecting data from cancer immunotherapy to scale out what they have been doing, take all the experience from Sloan, the Sloan data management, and essentially we covered at this point, we analyzed 38 trillion pixels of cancer data. The Sloan survey was about 8 trillion pixels altogether, and we did this, with a handful of us. And then recently, we stored the world's largest ocean circulation model created in collaboration with Chris Hill from MIT, and we just released 4 petabytes of data for interactive access. So, universities are capable of creating such data sets, and you can see that essentially the expertise that we gained with Sloan can be translated into other domains successfully. So, but we are getting too good in generating and collecting data. So if I ask you, do you have enough data or would you like to have more, everybody would answer, I want more data. Okay, but I didn't specify what data will you get. And so it's the wrong answer to any of those questions. And there is this delicate trade-off between the value of the data and our budget. And if we collect too much data, then we basically blow our budget on these drives and there is no need to pay for the science. And the other way is also bad. So particle physicists have been faced with this for a long time on the LHC. So the challenge was find a needle in the haystack. And the Higgs was a needle that they didn't know how the needle looks like, but they knew how the hay looks like. So what they did basically create a very detailed Monte Carlo simulation over 10 years on the computational grid. And this was representing essentially the corpus of known physics. So these are the events that we already know about. And so they set up filters on the beam lines in the detectors where they only keep those very rare events which actually which look good, and at the same time, they don't look like the old physics. And so they keep only 1 out of 10 million events typically, and this is still 10 to 100 petabytes, and keeps the whole world's particle physics community busy. And my prediction is that very soon we will have to do this with every experiment that we do, because we will have data acquisition systems where the data can flow at such rates that if we wanted to capture it all and think about it later, then we will be overwhelmed. So the only question is whether we don't have to do 7 nines down select, but whether we do 9 to 1 or 99 to 1 or 999 to 1. So we can use AI to collect much more relevant data. We should use AI before and while we collect the data. And it's happening at CERN. Maybe this will be the 5th paradigm of science, where algorithms control our experiments. And so Stuart is funding actually an experiment. We are working with the Japanese on the PFS survey, how we can create a feedback loop in the target acquisition loop so that we can have AI doing a quick look at the data after each exposure, and then we can retarget the fibers if we are off. Bottom line is that if an AI algorithm can drive our cars, why cannot it run our telescopes? And this is, something a revolution that happened just yesterday. So this is a new box released by NVIDIA. It's a 1 petabyte computer with 400 gigabit ports, a Blackwell chip, 240 watts, 128 gigabytes of memory and 20 cores. It can run the smaller language models. It can run Llama. And I predict that each of these machines can run a generative AI next to every microscope in a lab, basically, and then use it to filter the data on every telescope. And this is actually not very accessible. This is it. So this is a petaflop computer. That's for $4,000. So I stood in line yesterday at Micro Centers to get the first 3 that are to Baltimore. But I felt the same kind of excitement when I got my first IBM PC.
Do you understand the line?
Yeah. So anyway, so I think as William Gibson said, the future is already here. It's just not evenly distributed. So I would like to hand off to our next speaker, Stu, who has been also at places where the future was generated. And he authored one of the most used pieces of software, the Make utility.
I have. Yes. Let me just a small delay.
Whatever has to be done gets done. Thank you. I'm just going to be making some very general remarks. I'm happy. Feel free to shout during or after and make comments or questions or whatever. Thanks. Alex's comments were most interesting. I go embarrassingly far back in computing. My first course was when I was 11 on a vacuum tube drum computer. You can try to imagine such a technology. Probably you can't. However, the curve of growth, of change is breathtaking. Alex was telling me about his coup of the morning, which you just saw. I still can't quite believe it, given. But I remember one day when I was working at IBM and threw a couple of laptops in the trunk of my car. I just looked down at them, and these were machines that were running at something like 33 megahertz. And I realized that I had more computing capacity in the trunk of my car than the world had in about 1955 or 58. And I just thrown them in the trunk. Now, here we have something operating at 5 orders of magnitude more than the trunk of my car from that period. And wow. Okay. Another interesting comment, Alex pointed out that the AlphaFold and type work built on $20 billion worth of painstaking chemical research, actually making the proteins, running them through X-rays and all that. There's an interesting new phenomenon.
Is this working? Can anybody hear me? Does anybody want to hear me? No, I shouldn't ask that question. However, I'm more comfortable wandering since I need a little energy. However, there's been a very interesting other curve some colleagues did a few months ago, which shows the submission of new data into the protein databases. What do you think that curve looks like? It looks like that. It fell off a cliff. When you the incentive to do more of the horrible chemistry and the very difficult crystallography and all of that is now that you add one teeny bit to the input of DeepMind and the protein database work in Seattle. That's your credit. People say more or less, why should I bother doing that? I can do something interesting instead. Or I can go and sequence some really unusual chemical and perhaps do something entirely different. So there are really interesting social feedbacks that can follow from the great things that we do. And whether that's a net positive or negative for biochemistry is outside my personal scope. However, let me just hit on, say, just in essence, this is a summary of what I'm thinking of talking about today. I don't think anybody here is going to disagree that scientific software is really important and actually, I would say, increasing importance. It both enables more efficient research Alex's observation here that putting an AI model next to every expensive instrument is probably now a no-brainer. Demonstrated with a $4,000 credit card purchase, not a large 10-year NSF competition, which, by the way, would have been what you did 10 years ago to get that much computing. But also, scientific computing is the only way we understand anything about complex phenomena today. 19th century mathematics brought us great techniques for understanding linear equations. Unfortunately, the world ain't linear. And once you get nonlinear, unless you're Gauss, you can't do anything with the mathematics. And so you might as well just compute. There's no closed form anything anymore. Real engineering is needed. Quick and dirty code can last a long time. You're looking at a proof of this. I wrote the original version of Make over a weekend in around 1976, and some of you are probably still using it. The code is appalling, and I wrote it myself. And when I looked at it a few years later, I couldn't believe what I'd cobbled together. It's been rewritten by more professional workers and many things over the years. However, something can last 50 years. That is terrible. Okay, certainly it's had more maintenance than it ever had thought. In the original period that I did. I wrote it one weekend, I rewrote it the next weekend. And that was my contribution to making the world better or different. Yes, I'll just put in the apology for the tab in column 1, and you can ask me later if you want. I've apologized hundreds of times. But how do you improve the situation? Well, I mean, you can use technology, you can use education, or you can use specialization and professionalization. All of these are good ways to get the software that you actually need and deserve. And then I would like to comment just on institutional roles, since these days I sit in a very privileged place, philanthropy. So I operate under a very different set of constraints and opportunities. And I say I because I and my colleagues can actually make some decisions and just do them. And so let me comment on some of these points as I go along, if I may. Just a quick detour. I currently am President and Chief Scientist of Schmidt Sciences. We have about 55 staff as of yesterday, when one of them was led in the country. Yes, I currently have 2 staff who are marooned in Australia, waiting for the U.S. government to reopen. And we can go on and on that. Legally, this is a new foundation created 18 months ago, funded by Eric and Wendy Schmidt. I've been actually working for them for 10 years, giving away their money for science on an exponential curve. We currently give away a lot of their money, and I hope, I had a review just yesterday. I'll find out what they think. We aim to have a big impact both on science and with science. And we tend to focus in a small number of areas with significant funding. Significant funding meaning, every one of the areas is many tens or more of millions a year. And the main areas in which we work are improving the science system. We have a bunch of fellowship programs, some of which you may have heard of. Basically, at the moment, we fund about 300 postdocs a year. For example, and climate research with a goal of having good enough climate understanding by the end of the decade with enough precision that you can know what's going on and know whether something is working or having an impact. Right now, both the models and the observations are surprisingly insensitive. One of the more shocking data comes from March 2020. Roll your mind back to that period, and you may remember doing nothing. You're right. COVID had just hit. The world shut down in reaction, and most of the industrial world basically went catatonic. Nobody went anywhere. Nobody did anything, et cetera, et cetera. Their estimates of how much carbon was not emitted for a few months while the world slowly re-equilibrated. None of that is observable in the climate data. We know that the carbon wasn't coming up, but we couldn't see it, and we couldn't measure it. Well, one should worry about that now. And there are multiple possible explanations. None of them are fully understood. Some of them, the rest of the environment simply decided to put out more carbon dioxide to make up. It's a risk. The oceans have a lot of options. Or maybe our measurements from space aren't very good. Or ... Okay, if we don't have models that can notice 2.6 gigaton divot, we have a problem. Okay, that's one of the goals here. Biosciences, we're looking at non-medical advanced uses of bio for industrial type problems and asking what are the reasons we're not doing as much of smart biology to make stuff. One can get much more scientific than my statement, obviously. Astrophysics in space, which is a personal interest. We are basically funding observatories, funding data, funding analysis. I hope that we will be supporting 3 or 4 new observatories in 2028, which means more than any country will be doing that year, as far as I know. And 2 of them will be generating awesome amounts of data. One of them will be an continuous optical survey, and one will be a continuous radio survey of the sky. And radio astronomy is pretty amazing. The raw data rate that will be coming in from the antennas will be a fraction of an exabit per second. And that was not a mispronunciation. There will be over 1,500 large antennas filling a valley. We're not just funding small science, turns out. The valley itself is 150 square miles. And also interested in space opportunities. And then AI and advanced computing. We have a bunch of very interesting efforts, some of them here. And I'll talk about that in a moment. But we have specific focus work at the moment on trustworthy computing, AI in the humanities, AI for science, a bunch of general efforts in understanding what AI does and how it can do it, and the impacts on labor and the economy. Being careful here, we only do science and hardcore work. We don't do policy. So the economics work, for example, is actually funding studies to see what actually happens instead of what people think might happen. These are probably disjoint. Sorry. Okay. Just for local relevance, I mean, some of the things that we have supported here, petabyte storage and the OSN efforts that Alex started many years ago, an assortment of interesting projects by Brees and Sean and Josh many years ago. Of most relevance here, the Virtual Institute for Scientific Software Centers. We have 4 of them. One of them is here, where we are basically funding a bunch of engineers to do work scientific software building and advising mostly for our other scientific awardees, and then of course some at Hopkins in this case, and a very successful center it is, and it's embedded in IDEAS. So thank you, Alex. And then Alex mentioned the optimization of the Subaru spectrograph, which is a very deep mathematical question. We're probably going to pick up support of SDSS. We're probably going to buy some significant computing resources shared with Hopkins coming up. And various other items at the moment. There's at least 3 AI 2050 fellows, and there have been 4 Schmidt Science fellows, and there's an AI safety project underway. So these are just the things that Schmidt Sciences has done with Hopkins. These are not because we have a Hopkins budget. Every one of these things was pure merit and usually brutally competitively chosen. And the list is not complete. I got this list by walking up and down the hallway yesterday and saying, can you check to see how many projects you have at Hopkins? Because I had forgotten. And I'm a member of the soon-to-be operating, I hope, advisory board for data science, now that the director has been named after a rather long search. This is a tough market for good people. And Schmidt Science Fellows, I just mentioned that Denis Wiertz has been a long-time reviewer and friend of that program. So just for any local interest. So, sorry, I'll take a 2-minute personal digression. Just, I've been a computer programmer essentially forever. I mean, the first course I took was when NSF was actually useful and supporting summer programs for young people. And I ended up at the Columbia Science Honors Program, and admission was purely by a written test, and they forgot to have an age limit. And so I and a few friends who were pre-bar mitzvah, literally, got in. Okay. My mind was warped totally by a vacuum tube computer. I'm sorry, I can still remember some of the numeric opcodes from the IBM 650. If you want the truly wasted gray cells, that's it. The odds that I'm ever going to want to do any of those operations again is pretty low. But never mind. My academic background is in astrophysics and applied math, but I went bad, and my career was in software, Bell Labs, Bell Communications Research, IBM, and then Google. In other words, essentially the best places on the east coast of the U.S. Out of academia. And I have taught courses, but I've never been a professor. So that has that distinguishes me somewhat. Those of you who are interested, I did indeed write Make. I did write the first Fortran 77 compilers. I did things with Silicon compilers and other good stuff. My attention span is about 3 years if I look at the sort of correlation times across interests. But I've been interested in scientific related computing. My PhD thesis was, and my undergraduate work occasionally involved doing some numeric computing, even though my PhD supervisor was one of the finest applied mathematicians of the last century and a totally analytic, non-computational person. So it was a fascinating tutelage. Where I was working at Bell Labs in the summer or during the year playing with computers and doing messy integrals and expansions during the day. But at Bell Labs, for weird organizational reasons, I ended up in the numerical analysis department. So I was sort of raised by wolves. And so some of that wore off a bit since half the discussions were, screaming at partial differential equations and such. But at a different scale. I was for some years on many review committees at Los Alamos, and I'll just say that they did indeed operate at world level scale, and I learned a lot about good and bad ways to organize software engineering by watching other people. And at Belcore, I eventually realized that software engineering and serious software engineering began at 1 million lines of code. Although small codes are just a different world. And scientific computing used to be all small codes, stopped being true a long time ago. Okay. And now for 10 years, I have been working for Eric and Wendy Schmidt, originally as a consultant, and then building up a significant effort and basically convincing them of things they would like to support, and they have been incredibly generous. We don't quote numbers, but my budget is several hundred million. And I find myself running one of the largest non-medical science philanthropies in the country. Now, scientific software, just comments that I think everybody here will probably just cheerfully say, "Why am I bother saying this stuff?" It's central to much of science. The third and fourth paradigms, simulation and data-based science. Those terms are so old that most scientists don't realize that anybody thought they were a new idea. It's quite wonderful to see revolutions become history. But if you ask, so where's software? Control and analysis experiments. People don't sit there with a pipette and just go drip, drip, drip anymore. If nothing else, you use a machine that does 96 at a time. And doesn't go drip. And then you can't operate experiments, you can't operate large equipment, you can't even operate small equipment anymore by hand. At which point, all the questions of reliability, certification, provenance come in. The complicated theories, which is all of them, basically, can only be explored numerically. Nobody can solve gauge equations. Nobody can do the climate, etc. You can say that there's been only slight progress in climate science, in that Arrhenius had the correct answer within a factor of 2 on the grossest number in 1909. However, if you actually want to do anything detail and know what's really happening, then you need to be an order of magnitude better than we are today, as I suggested earlier. And there are areas of climate prediction and modeling where, to put it politely, the error bars cross zero. In other words, you don't know the sign of the quantities you're talking about. And that should bother you, perhaps, if you read about climate forecasts, that you may not know whether something is helping or hurting at the moment. Literally, we believe that you can shrink some of the key error bars by about a factor of 5 with a lot more research, and we're funding a lot of projects at the moment to try to narrow those error bars, by the way. And enormous data. Alex pointed out what the data rates are from the LHC, and if you don't it's not that they feel like throwing away all but 1 out of 10 million events. There's no choice. These things are happening on the nanosecond time scale. You can't store them, even if you wanted to. And then there's no place to put that much data and keep it. So now there's now a serious set of worries in the last few years. How many needles did we throw away when we threw away all that chaff? And so they actually do have some samples where they don't throw away everything in order to reanalyze, in order to see, are there any interesting events that don't look like a Higgs boson? The original searches were quite specific, after all. So physics is basically driven by models that can only be discussed numerically. And now, can you trust your numerics? As I said, I was raised by numerical analysts with wonderful stories at lunch about computations with 0 bits of precision, which now comes back when I look at this machine over here, which indeed is doing on the order of a peta-op a second, but it's on 4 bits of precision, which in the old days we called none. Okay. Yes, I do understand why. So anyway, AI, however, now adds another level of scale, complexity, and nonlinearity. And we don't really understand the implications of this yet. We know applications, but not implications. So, let me, however, bring in the word engineering, which I think is the most important topic for many people don't get right. Yes, I was raised as a hacker. There was, as a kid, I used to program literally at the key punch machine. I would write the code and type and punch the cards at the same time. I do not, those of you, a card is, by the way, a piece of heavy paper into which holes are cut. You may never have seen one of these in reality. It's a technology 1 level after clay tablets. Yes, I did it one time, use punch cards and so forth. I don't miss them, just by the way. Basically, software for science is a real mess. Discrete, continuous mathematics, throw in control theory, feedback loops, statistics and probability, and then cross that with data and cross that with real time and embedded. Everything ends up in the mix, and then it's got to be correct. You've got to be able to convince people it's correct, or you don't worry about it and you just publish anyway and hope for the best. Both models have been executed frequently. It would be nice if we did more of the stuff being really correct. And one of the outcomes of the replicability crisis and at one level and the drive for open data is that people can go check your work. People can rerun models and A, note whether you fudged, and B, whether you got it wrong. And so, there are lots of interesting examples. I mean, there's a quite drastic one in economics that you may know, the Rogoff and somebody error, mistake, which was an error in spreadsheet computing, which is not normally viewed as scientific computing for very good reasons. And the result drove errors in national economic policy. It basically indicated that inflation didn't matter up past a certain point, and it was a result of not adding up the numbers correctly. All right. Now, how many errors do we want to discuss in biology or chemistry that are perhaps more to our taste? So the need for credibility and correctness is actually more and more serious. Thank you. I will. But engineering is traditionally is about the ilities, reliability, availability, maintainability, adaptability, flexibility, etc. And these are boring. It's really neat to show beautiful graphs appearing in many colors on your screen, and good fun like that. The reality is, if you don't believe any of this stuff and you can't keep doing it, you're in big trouble. This is what engineering is. It's a mindset. It's a discipline. It's something I wish I'd had as a kid, and it's something I have professionally been pushing and working hard on because of that. there is this weird category, which many people in this room probably are in, of research software engineer. I say weird in that it's only an academic category. In industry or mission laboratories, we just call the category software engineer. It's just an ordinary job category, not a glue-on to a 1,000-year-old industry. The University of Bologna didn't have any software engineers, so far as I know, in 11-something. But it's really important, and I should mention, we, and in this case, it's I personally and my colleagues, really believe in the value of professional engineers. I have seen the difference between part-time graduate student who's hacking away to finish something and a research project which has full-time engineering workers doing the software. The differences are horrifying, of course. You may or may not think that the graduate student, fueled by adrenaline and caffeine, has more energy and more smarts than the software engineer or not. But basic rule: a graduate student has only one job, which is to get the hell out of here, and with one big piece of paper in and one piece of paper out. Whereas the code may live 50 years, as I just suggested. We fund at least 60 engineers. I just don't count anymore. The VIS centers themselves have over 24. We have a group at Caltech, which is a different model, Software Academy, which has another 10 or 12. And then we have projects which we cheerfully tell. When we fund a large project, we cheerfully say, sure, hire software people. Yes, go ahead and pay them. And the results are usually very gratifying. So, and we will have more. And this is not a movement. It's just a practical response that if you want great software, and we typically fund, most of our major projects tend to be $1 million or $2 million a year for 4 to 6 years. That means that the software ought to last at least 4 to 6 years, and that it should be usable by more than one generation of postdoc. That means having some professionals in the spine, and we really believe that. So let me just comment a little bit on AI, which is, I assume, going to be an ongoing topic all day and all year. And I'll just note the double arrow, AI and software engineering. At one side, there's software engineering for AI, building the large model systems, building the more complicated inference engines, and so forth. This is heavy-duty, very scientific computing. In the back room, you're doing steepest descent, even if you're doing it with 4 or 8 bits of precision, with a lot of delicate correction factors, of course. But there's unprecedented scale. There's performance requirements that are enormous, and every so often there's a big shift in that, of noting that if you're doing a computing run that costs $100 million worth of hardware, then 1% improvement cheerfully pays for your engineering effort to have done it. But then you get end runs like DeepSeek, which by doing a different approach, we got a factor of 3 or 10 improvement in certain aspects of the problem. So rethinking what's going on is deeply important, and I'll get there in a moment. But the need for high precision in parts of the compute, and the fact that some of the computing is being done with 1-bit precision, just an estimate of the sign estimate, and the fact that we have closed systems which which you just have to take on faith, and what could possibly be wrong with a system that generates 100 million parameters, each of which no doubt is checked by eyeball. Okay, yes, and this has been going on for 10 years. So yes, you need therefore real engineering discipline that's going into validation of the computing, because nobody can check the answers other than, oh, it did that. That's interesting. And the whole new world of inferencing, which is getting into iterative computing, getting into more low precision. On the other side, there's AI assistance for software engineering, and that's going to be inscrutable at the moment. Co-pilots and such being the generic term. Yes, I know there should be a trademark on that, but never mind. And testing approaches. To what extent is testing designed for testability itself still relevant in an AI world? To what extent can AI do it for you? To what extent do you believe the AI just did it correctly for you? Why should it not be hallucinating your test results also? Okay. And understanding error propagation. What are the impacts on different levels of user? There are all these questions which are coming back in a world where we're depending more and more on AI helping us to do the software. And then you can look at which studies you like that say, how much does AI, how much do co-pilots, how much do frameworks improve or unimprove the code? To what extent do they speed up or slow down the work of the best and the not so best programmers? And unfortunately, it's not a balanced curve of best and not so best. It is not a symmetric bell curve, I'm afraid, but rather a heavily weighted curve. But then you've got, does AI just replace software? If you just ask, what's the answer, and it gives you the number, and magic happened in the back, has that simply gotten rid of software engineering entirely? Well, if you're credible, it did. I'm not that credible yet to believe that it did the right thing, and figuring out how you know what got done. So there may be in certain areas less code written, but we are now going to be back in the validation world and the engineering world in a whole new way. And that has not yet been addressed fully. Alex pointed out the timescale issue here, that there are radical changes in AI every year, and significant ones every 3 to 6 months. And we may be on a slight slowing of that because, GPT-5 is not radically better than 4. However, 03 changed the world as people started thinking about AI. So anyway, this is the enticement from my point of view. What is really going to happen over here? The software engineering to build systems, that's interesting. This is the mass implication. How do we get software written? How do we get answers created that are credible and prompt? So let me stop here and have people throw things at me. Thanks.
Questions?
So the AI approach is kind of useful possibly in trivial cases, chatbots or whatever. But at what point are they going to be useful in serious decisions like potential diagnosis or something like that? I know that there's lots of options for trying this, but would you trust your scan to go through AI or not to a radiologist as well?
I'm sorry, I'm in the middle in different diagnoses from 2 human doctors who are specialists. The idea that I'm going to have to hire a 3rd retinologist to debate with the first 2, I'm not sure that I'm better off than with a Ouija board or with an AI system. So sorry, this was last week.
Right.
Yeah, and they disagree on the same data. Thank you. All right. So actual studies do suggest there are areas in which the AI systems are already superior to most clinicians, and
And maybe that distributional programmers is also applying to clinicians.
Oh,
And everything else.
absolutely true. So when I was about a dozen years ago at Google, one of my colleagues was doing a study actually of eye exam data. And in order to be able to test the computer vision system applied to vision, they did a lot of expert testing. And the data they got on, to be polite, intra and inter-rater reliability was mortifying. Yeah, basically, you take these pictures and you show them to experts, and some of them you show to the same expert a week apart, but you show them a lot of pictures so nobody can remember. Oh, I saw that one last week, and so you should give them a pile of 100 and tell them to re-rate them, and intra-rater reliability was about 70%. The same guy. Between raters, it was 60%. Okay, never mind. The AI system did not have that problem.
No, that's a nice statistical property to have, right? Interchangeability.
Yep. You can get any number you want, but if you ask enough experts, we know that. Okay. Well, so I'm sorry. I'm giving you anecdotal answers, of course, but there's a whole bunch of areas where, yes, I will trust the machine more than most people. On the other hand, none of them no AI system will I trust more than an experienced plumber, because plumbing is hard.
So Stu, Alex, after holding up that NVIDIA box, said, the future is here, but it's not evenly distributed. And so there's this irony confronting us where we're in this era of cultural changes and open data sharing and the availability of large data sets for all, but we're still in the time where the sorts of resources needed to get the science out of them aren't evenly distributed. Do you want to say a little bit about how you view that through the lens, for example, of your work at Schmidt Sciences?
Yep. We have, let us say, a fairly strict view on open data. We like it a lot. And if you don't want to make your data open, you don't have to take our money. It's a simple policy approach. Sorry. So on the other hand, not everybody can stand in line and spend $4,000 to buy more computing than the world had 20 years ago. In that box. Okay. But that says that that computing capability is being distributed much more rapidly than you would expect. Access is real. The internet reaches everywhere today, and there are actually pretty big pipes into all continents except Antarctica. And even there's I don't know what the military bandwidth might be. So it's not actually as dismal as it looks. Being on the leading edge will always be a leading edge activity, and that will not be uniformly distributed. It helps to be rich, to take risks, and to be wasteful. But to be 2 generations behind on something where a generation is a year is not actually such a bad disadvantage. And so if you're talking about using these techniques, being a little behind and a lot cheaper is better than the traditional world where it was generational to shift technologies. So strangely, I am not as disturbed by this phenomenon as many people. Yes, of course, separate issues of, it's hard to use advanced AI if you're starving to death. And so, let me introduce all the world's economic and medical woes as a separate variable. But computing is a surprisingly democratizing phenomenon. Now, if you want to say, can I build a world-class training model, then it helps to have the cache hoard of Google or Microsoft. If you want to use one of those, you need a credit card. Or if you want to use it a little, you don't need a credit card. Well, that's a pretty good deal for the world. And it's not yet clear that those leading edge models are going to be the dominating moat for competition that the large companies are betting on. So, and these views are then crossed with, we happily support open access and open use. The center of mass of our funding and climate is outside the US at this point. A quarter of our awardees in several of our major programs are outside the US, and that number will increase over time. So most of these are not in the, quote, emerging countries. We have actually a separate program for providing AI knowledge to some people from the global south in an extension of our AI science postdoc program. And we'll see which model works, and then we'll build on it. So we are experimental here, not dogmatic. So giving a very personal and organizational answer rather than the whole field of philanthropy.
Thoughts on what to advise?
I'm sorry.
Oh, Stu, I'll give this to him. We'll do a little bit of musical chair.
Hey, I'm Duncan. I run the Cryo-EM Center down at the School of Medicine. But I had a question about students and the kids growing up these days. So as AI replaces a lot of the trivial stuff that they used to sort of like enter into, do you have any thoughts on, or have there been discussions about what to advise them to study now? And how to sort of like...
Let me not get into that at all, because, sorry, I commented I've never been a professor or a official teacher. And so, standing in a major university, I feel a little embarrassed to tell people how to teach or how to learn. Clearly, there are the challenges to the traditional education model are drastic, and that's good. I remember many years ago during a boring lecture trying to do long division. And boy, was it hard. I just wanted to divide, for weird reasons, I had a 5 and an 8-digit number that I wanted to divide. And my reflexes wouldn't come back. Again, they'd been really good when I had been in 3rd grade. But I hadn't done long division since about 5th grade. Okay. Did lots of things that we do. I was horrified to realize that the electromagnetism book that I studied from as an undergraduate, Jackson, was still in use. And I took a look and basically said, why in the name of God would you be studying those expansion techniques anymore? Why would you be interested in that rather than just the obvious numeric solution of the equations, which anybody can do on essentially a wristwatch? Well, now move that broader to this little box. Rethinking what's relevant is just going to be tough. I'm not going to get into the cheating, plagiarism, etc. Parts, and the general theory that if you don't sweat hard, you don't learn anything, which is probably true. I agree. I think the education is going to, on the one hand, easier. Cheating is going to also get easier, but I think answering the question of what should I do with my life to be productive is going to be a different problem than I was hoping. Maybe you had a feeling for like what you saw is places that need an actual human going forward from the high level 40,000 feet. Let me not be speciesist. Why do I care about humans if we have if our successors are already being put in little boxes? Okay, speciesism is going to be a separate topic. Okay, on the other hand, we do have a self-protective interest. So Various economists have assured me that economists are extremely good at estimating what jobs and what tasks will become obsolete and no longer worth doing. And they're absolutely wretched historically in figuring out what's going to replace them. And it's, Otter et al. Did a really interesting study at MIT. We funded a tiny bit of it, which looked at the rise of new occupations, basically looking at the annual business, the decennial business census data, and seeing what the new categories were. And 60% of the jobs that people are doing didn't exist 3 decades ago, and nobody predicted they would show up. So. I think that humans have demonstrated a total inability to answer your question. Whether our masters will do a better job of such forecasts, I don't know. I'm dodging completely because we really, really aren't any good at this. We are funding a half dozen RCTs to actually try understanding what the impacts are of applying AI in real world situations, not on business class or psychology 101 students. And because a lot of people have talked about it, but nobody has any good numbers. And we're hoping to pay for some, just by the way, because we're intensely interested in which parts of these stories are right and which wrong. So no, I do not know what I would advise a 12-year-old to study. I mean, the only time I've ever been listened to was by a nephew who was thinking of, he wanted to be a radiologist, and I said, don't. And he chose something smart, dermatology. Dermatology doesn't have any weekend emergencies, and you have to touch. So it's relatively immune to AI for the short run. And radiology is probably gone. Yes, but at a very high level, I can assure you no one knows. I should probably have mics.
So thank you very much.
Our next talk will be given by Edward Hunter, Director of Engineering at the Scientific Software Engineering Center at Johns Hopkins. Edward Hunter holds a PhD in Electrical and Computer Engineering from UC San Diego and is the Director of Engineering at the Schmidt-funded Scientific Software Engineering. It just said that. Okie dokie, Edward.
This is working.
Yes. And I can turn it up.
So I'll use that. Okay, great. Good morning. Thank you, Sam. So my name is Edward Hunter. I'm the Engineering Director at the Data Science and AI Institute and the Scientific Software Engineering Center. Today, I'm going to give an update on research software engineering at DSAI and SSEC, and I'm going to touch on these items in my outline here. So first, I'll go over an overview of the organizations and the relationship among them. Then I'll describe some research software engineering programs we currently offer and some that are in development. I'll introduce the technical staff. And towards the end, I will give a summary of the projects we've engaged so far and give a couple of examples to kind of make that a little bit more concrete. So the organizational relationships are a little bit complex, so it's good to start with some context. As you probably know, DSAI is intended to be a major force in the AI and data science space in academia. It's an umbrella organization that spans all of the JHU schools and departments. And departments and centers federate with DSAI, which basically means that they share resources like access to administrative support and hopefully ultimately access to shared grant overhead funds. DSAI is broken down into three main components. There's an academic component, which is home to the intellectual home to the DSAI faculty, who have the responsibility to set the research and education agenda as it pertains to data science and AI. And then there's the infrastructure component, which has the responsibility to expand the shared JHU compute systems. Those systems, the composition of those systems is currently evolving, but the latest numbers that I've heard are that it will include at least 1,000 high-end GPUs of various denominations, over 100,000 CPU cores, and over 200 petabytes of storage. And that places these JHU systems in the cluster of top academic systems nationally, maybe in the top 5 or so. Then there is the engineering component, and this is a little unusual. This is a team of research software engineers like Stu Feldman was describing. And they have the responsibility to support the DSAI faculty projects. There are 9.5 RSEs on DSAI staff right now. That number will grow to at least 30 and potentially between 45 and 60, depending on the success of the program. While their primary function is to support DSAI faculty projects, we can also support general JHU faculty projects as time permits. Then there's SSEC. SSEC is one of the 4 VIS centers that is funded by Schmidt Sciences that Stu mentioned. It's a unit within DSAI engineering, and it has a very similar mission, except that we work on projects that are selected out of the Schmidt Sciences network of scientists. And those projects typically have not as narrow a focus on data science and AI. There's 6.5 RSEs on staff at SSEC today, and 2 of those are borrowed from IDEAS. Project differences among these organizations revolve around how projects are selected, like I mentioned, how they are transitioned and sustained long-term, and also the project duration. SSEC typically targets short-term projects between 6 and 9 months, ideally. The DSAI sponsored projects start out at 2 years and can be extended up to 5. What is DSAI and SSEC research software engineering? I like to think of this as a collection of programs in service to the vision. And so I've listed the visions of the 3 organizations in paraphrase at the top there. They're all very similar and complementary. All of them involve software development, data analysis, and application of compute and scientific discovery. So the differences are mainly a matter of emphasis. And so the flagship programs are the RSE services, and these come in a few different flavors. First, there are the institute-sponsored projects. These are available to DSAI faculty at no charge, and they're awarded through a competitive proposal process. Then there are fee-for-service projects, and these are typically funded by faculty grants. Then there are projects we do with strategic partners. SSEC and Schmidt Sciences is an example of this. Another partnership we have is with the Cancer AI Alliance, where a consortium of 4 organizations is working together to develop federated learning technology for cancer research. We also have an office hours program to provide technical advice and consulting. This is free of charge and available to all the JHU faculty. And then looking into the future, we have a few programs in the planning stages right now. One of those is an RSE-led short course training program where RSEs develop and deliver practical technical material in a short course format to the community. on material that's not adequately addressed by the formal curriculum or the various professional education programs. And then there's two different internship programs that we're working on. One is a department internship support program where RSEs will act as essentially teaching or lab assistants and helping students as that are enrolled in an existing department internship. And the final bullet there is an internal DSAI internship where students will come to us, work alongside our RSEs on the DSAI faculty projects in exchange for academic credit that would last a semester or two. Let's see. This is the DSAI and SSCC technical staff. I wanted to make sure you see their faces. Many of them are in the audience today, so when you see them, make sure you say hi and introduce yourself. The combined team size is currently 16, and we have 4 positions open. I don't show the IDEAS team here, but I do indicate on my notes who has come from IDEAS, and it's difficult to overstate how important the IDEAS partnership has been on the progress that SSCC and DSAI have made in the last few years. Some background on this group. 75% of these people hold doctorates. All of them have years of professional software experience and industry best practices experience. The range of experience is between about 4 and 29 years, with a median of about 10. And besides IDEAS, prior employers include some familiar names. So like Vectorworks, IBM Research, Microsoft, Roche, AWS, Sandia National Labs, JHU, Human Language Technology Center of Excellence, and JHU Bloomberg School of Public Health. This is a list of projects that DSAI and SSCC has engaged so far. You can see this list is pretty diverse. In some cases, we provide pure software engineering services. So things like build me a web application, build me a user interface for my existing software, help me design a data model and implement a database to hold my science data with efficient queries. So straightforward things with low risk. We've done them before. In other cases, we have a much deeper engagement and contribute to the research goals as well. So you can think of these RSEs kind of like postdocs or research scientists that can join your team on a temporary basis and help you achieve your science goals. The areas where we have expertise, indicated by these projects here, include data modeling and database design, scalable big data architectures, machine learning model development, NLP, computer vision and LLMs, hardware control and sensor networks, bioinformatics, microscopy and pathology, drug discovery automation, full stack and web app development, and GPU optimized algorithms. Okay. In this last bit, I'm going to show a couple of those projects in a little more detail to give you a more concrete feel for our work. This project is the automated creation of 3D tissue atlases. The PI on this is Ashley Keeman at the School of Medicine. And the goal here is to take a centimeters wide piece of tissue or organ, section that very finely, and then fix it and stain it, scan it in, and then align and reconstruct the volume digitally. There's also a deep AI model in the pipeline that classifies the tissue type way down to the subcellular level. That's what these images are. This is discrete tissue type categories. And so this is mouse lungs. So the image in the upper left, the orange one are the bronchioles. The red image is the vasculature. Pink image beneath that is collagen. The gold speckles of tissue are cancer tissue. And I have a short movie that shows the results of this processing and our interface, if I can get it turned on here. So this is the user moving up and down through the volume along the z-axis. Again, the colors represent the different tissue categories. Here we're navigating in 3D around the object. In a moment, we'll select out the bronchioles for a more detailed examination and a zoom in. So for this project, we started with a crude research prototype in MATLAB. We re-architected and re-implemented everything in a clean Python package. We added visualization tools like this. This is a framework. We based our visualizations on the Nippani framework. And we made improvements to the processing pipeline and the segmentation model itself. Okay. Great. This last one is a little more abstract, but just as scientifically interesting. This is the surveillance of mortality in rural Mozambique. The PI is Igbezi Amuzu at the Bloomberg School. The goal here is to use AI to provide cause of death estimates from next of kin interviews. And it's important because it allows these countries with poor healthcare infrastructures a feasible way to estimate cause of mortality statistics across their population that they can then use to assess their policies and direct where future resources go. So we did a high quality study of modern machine learning models applied to this problem setting, and that hadn't really been done before adequately. We found that some modern AI models, those based on gradient boosted decision trees, achieved a new state of the art on the gold standard data. They beat the most commonly used prior models by up to 9%, the 90 times speed up. The common models in this area are Monte Carlo approaches, which accounts for most of the drastic speed up that we saw. And we're currently looking to move these models into the transfer learning framework that the PI uses. And we'll then also expand the study to further evaluate and baseline modern transfer learning and self-supervised learning techniques in this setting. That's a very appropriate place to do this because this is one of those machine learning settings where the labeled data is very rare and expensive to get. And there's lots of distribution shift between where you collect the data. So this work was a lot more on the research side than some of the others. Okay, that's the brief overview. These are the main points to take away. Thanks very much. Please feel free to reach out to apply to our programs and reach out to us if you have questions you'd like to ask or you want to talk about your research in more detail. Be happy to do that and happy to take any questions.
That was great. Thank you so much. I'm interested in a lot of things. One thing is the programs where the RSEs are connected with Hopkins faculty, whether it's, pay to play or supported by the Institute. How do you make the matches between the RSEs and the faculty? Are your staff already divided by discipline, or is it something else?
Yeah, good question. In the case of the sponsored projects that come in, those that are scored highly and likely to be awarded will get passed off to us, and we will review if we have the correct expertise to support that. That basically guides it. And then we'll have an introductory meeting where the teams get together and take it from there. So it's basically about what expertise we have, I guess. It can be both. Sometimes they need domain expertise in an area. Almost always they need technical and software expertise in an area. Depends what their goals are. Yeah. Okay, thank you.
right, our next series of talks will be updates from the 2025 IDEAS Seed Funding Initiative. To facilitate multidisciplinary collaboration, this was a program where IDEAS offered Hopkins principal investigators the opportunity to secure up to $25,000 in funding for research projects that involve data science and data-intensive techniques and analysis as part of their core research. Seed funding recipients work in multidisciplinary teams to build ideas with good prospects for successful proposals to attract external research support by leveraging IDEAS' intellectual and physical infrastructure. This year, we awarded 4 seed funding grants. Each of the recipients will give an update on their work. Our first seed funding update will be given by Jung-Hee So. Dr. Seo is an associate research professor at the Johns Hopkins University Department of Mechanical Engineering. His research is focused on the biological and biomechanical fluid flow, and his expertise is computational modeling of multiphysics problems, including fluid structure, interaction, acoustics, and chemical transport. He received his PhD at the Korea University in 2006 and was a postdoctoral fellow at Stanford University's Department of Aeronautics and Astronautics. He joined the Johns Hopkins University in 2009 and performed research projects about human phonation, cardiovascular flow, heart sound, and flying and swimming animals.
Morning, everyone. My name is Jung-Hee. So today I'm going to talk about our seed funding project update. It's titled Estomach, Multiphysics, In-Silico, and Computational Model of Issues. I know that it's a big word name, but I just tend to put I. So yeah, this is about the scientific computing stuff. So Dr. Rajat is the main PI of this project. And that's called the structure, that clinical protocol. So yeah, we talk about the stomach and like it plays a vital role in our life, but its main function is digestion. So there you can see this diagram. Stomach stores food. Also doing mixing, breakdown of food, also making execution, juice, starting digestion. Thank you. Digestion. And eventually emptying the stuff to the duodenum and the intestine for the nutrition absorption. So we call this whole process gastric digestion. But in fact, this gastric digestion is a result of complex interaction between the multiphysics processes, as I've shown here. So there's a gastric motility, the motion of this gastric, the stomach wall, that's related to the biomechanics and tissue dynamics and so on. And there's a fluid dynamics inside the stomach. Specifically, this will be the multi-phase fluid dynamics and fluid structure interaction. And also there's, of course, the biochemical reaction between the food and gastric secretion for all the digestion process. Right? And then if there's something wrong in any of these physical processes, it can cause some problem in the gastric digestions. And the problem in gastric digestion is implicated in many disorders and illness, as shown here, so like nutrition or foodborne illness, or systematic disorder like obesity and the diabetes mellitus, or more regional disorder like gastric paresis and dyspepsia. So to get better understanding with all the origin of these kind of problems and to come up with a better treatment and even prevention of these disorders, it is crucial to understanding the biophysics inside the stomach. But such understanding is quite limited for now. It's partly because it's a complex multiphysics nature, but also it's because this in vitro or in vivo study of this human stomach is quite challenging. So this shows like a state-of-the-art medical imaging of the human stomach. It's called the cine MRI, meaning the time-dependent MRI imaging. You can clearly see like this the stomach motion there and some flow pattern inside with this contrast transport. So from this, we can extract like some morphology and motility. But it's still difficult to extract a more quantitative metric transduced by physics like force and pressure inside the stomach, or the flow or emptying rate, or even the reaction and dissolution rate, and so on. So our vision and the objective of this project is developing this image-based computational model of a human stomach. We named it the E-stomach. But at the same time, it's powered with this high-fidelity multiphysics simulation capability, the biomechanics and fluid dynamics, and biochemical reaction inside the stomach to simulate all this digestion process. So once we have such a model, this can provide like much insight into the detailed biophysics in the stomach. And also it allows us to investigate all these systematic and regional disorders. And even we could use this for the virtual bariatric surgery, the surgical planning and outcome prediction. That's the ultimate goal of this project. But actually, this project is originally motivated from the oral drug delivery study. So let me briefly tell about that. So, of course, this oral administration of the drug is most frequently used drug delivery route, but it could be the most complex way for the drug ingredient to enter the body, because now the pill or tablet will be inside this complex multiphysics nature. So the dissolution rate of this tablet or pill not only depends on its formulation or chemical composition, but also affected by all the stomach motility and the fluid dynamics and stomach contents, and also the fluid-structure interaction will result in complex trajectory of this pill inside this stomach that also affect the dissolution rate. So quite complex, but if you look at the actual dissolution testing device guided by the United States Pharmacopoeia, this is testing device type 2, will look like this. We have a container, rotating paddle, pill or tablet will be settled down there if it's heavier than water. If it's lighter than water, it usually cased there. And that's rotating the paddle at relatively high RPM and just measuring this dissolution rate. But as you can clearly see that it's quite different to real situation where the pill will experience in our stomach. So various studies already have shown that this device does not represent the real condition or flow pattern in the real stomach. But understandably, developing more advanced in vitro testing device will be difficult but also costly. So in this regard, if we make a virtual stomach model where we can test the drug dissolution in more physiological conditions, they will have lots of potential to overcome all this limitation of this in vitro type device. So we decided to develop like this virtual stomach model. So we started with this virtual population data set, which is the MRI-based anatomical data set. It's a good starting point if you have some idea on some biomedical simulations. So from there, we segmented out this GI system, so it's the esophagus and stomach, and this entrum, and the pylorus is the connection to the duodenum. But this data set is just only one shot, no time-dependent information. So for the motility, we use some data from the researchers and embedded this gastric motion there. So the key motion in the stomach is called the enteral contraction. It's like a traveling wave. This contraction is traveling downstream. It's very slow wave. It's only a couple of millimeters per second. It's traveling wave speed, and the pulse interval is 20 seconds. So we do have this baseline stomach model, and then this shows all the physics and bunch of equations we had to solve to model this drug dissolution in the stomach. Of course, we need the fluid dynamics equations, and also the motion of the pill or tablet is all 6 degrees of freedom solid body motions interacting with the fluid. But also it will be dissolved by the surface erosion, so that is modeled by this convective mass transfer. And also there should be the interaction with the contact with the stomach wall and the pill. So, and then all this multiphysics equations are simulated down multiphysics solver. Let me briefly introduce this solver. It's called BICA 3D, but the key feature of this solver is the immersive boundary method, meaning any complex geometry, by the way, this is left heart, can be immersed into the simple condition grid, but all the boundary condition and interface conditions can be applied very accurately using the so-called ghost cell method. The solver now can handle multiphysics, like the incompressible and compressible flow, and acoustics, and also the mass transfer, and chemical reactions, physics-storage interactions, and also the active material, the tissue dynamics. More importantly, the solver is well parallelized in the CPU and GPU framework and have shown the good parallel efficiency. So all the simulation is done with this solver. Now let me point out the key flow feature in the stomach. So as you can see, the body and the fundus part does not move much. So the flow strength there is very weak. It's colored by this flow strength, as you can see here. The main motility is this anterior part. As I mentioned, the main motility is called this anterior contraction wave, which is contraction is propagating downstream. But interestingly, that propagation results in this jet flow, which is flowing the other direction. It's called retropulsive jet. This anterior contraction wave and retropulsive jet are the two important factors making this the mixing and grinding of the food in the anterior region. And then with that, now this shows the result of this virtual drug resolution testing, the physiological setting with our virtual stomach model. And this one is like in the testing device, but we duplicated that with the simulation again, but a fair comparison, I would say. But you can clearly see the difference between those two. In this physiological setting, the pill is here, it's settling by this the anterior motions. The retropulsive jet is dissolving the pill, and the dissolved API is transported through the pylorus and into the duodenum and to the intestine. But in this testing device, while this paddle is rotating and the pill is just dissolving there. So as you can imagine, based on our simulation result, we observed that this testing device is typically over-predict this dissolution rate by 5 to 10 times. More importantly, with this testing device, we can only measure the dissolution rate. But with this setting, we can also measure the amount of this the active pharmaceutical ingredient transported to the intestine. That really matters. We can also measure that. So as you can see, there's a lot of potential in this virtual testing. And well, that was the reason that now the FDA approves the use of this virtual model, the so-called digital twin, and moving toward more this virtual testing in the regulatory process. So yes, and then now once we do have like this virtual model, we can investigate various interesting things because all the testing will be very easy in the simulation. So one thing we tried is the effect of body posture after you taking pill. So it will be important, especially if the pill is heavier than the water, then the gravitational force direction will be different with the stomach orientation and can affect on the dissolution and the drug delivery rate. So, well, we can just standing upright like this, or we can lean to right like this, or left, or just lying down. And then we can simulate all these scenarios, and this shows the simulation result. For the drug resolutions, you can instantly see that this posture 1, the leaning to right, really accelerate this drug delivery rate to the intestine, while the other posture leaning to left, really this the delayed drug delivery rate. It really matters, this body posture. And this shows the more quantitative result. This graph shows the API related to duodenum per gastric cycle. You can clearly see this posture 1, leaning right, this really accelerates this delivery rate, while this leaning to left is delay this delivery rate. So a very interesting result, and doctors agreed with our findings, and this result they aired through the news and media. So if you ever heard this kind of stuff, it probably originated from our study. So, and then this is also interesting. We can also look at the effect of some disorder, the regional disorder like the gastroparesis. Gastroparesis meaning like this motility problems. There could be neuropathic or myopathic problem that can result in the reduced amplitude of contraction or reduce the frequency of the contraction. So that can make these different types of gastroparesis. Type 1 has reduced frequency, or type 2 has reduced amplitude, and type 3 both. Then we tested this effect of this gastroparesis on the drug delivery rate with the simulations. Again, this shows in the simulation result. It is the frequency and amplitude and both. And again, this shows the quantitative result. Of course, this gastroparesis delay this decrease the drug delivery rate. But we have found that the reduced frequency has more impact than the reduced amplitude. That's also an interesting research we got. So, this was a oral drug delivery study we have done with the virtual stomach, and we found there are lots of potential. So, if we can develop this further to tackle the gastric digestion problem, we can investigate much more and many of the important problems. So that motivated us to further develop this virtual stomach model to the e-stomach models. So first thing, we included like a more patient-specific model development using the most advanced in vivo imaging modality, like the cine MRI. So with that, now we can take not only the patient-specific morphology, but also patient-specific motility as well. And then we're adding the more and more physics to simulate, like the electrophysiology and tissue dynamics. That'll be very important for the virtual surgery. We'll just cut these tissues. Very important to simulate that as well. And then to tackle this gastric digestion problem, you're adding the capability of food digestion simulations, liquid food and solid food, the digestion things. But more importantly, although we can develop this virtual model, but again, the credibility and the correctness, we need validation and verifications. Ultimately, it'll be great if we can validate our simulation result against some in vivo data, right? But extracting the quantitative in vivo data is always challenging. So there we could use like a data-driven method. Like we can set up the neural network to extract in vivo flow data from the MRI imaging. So I will explain this more details. So that is also the important part of the development process of the e-stomach model. So this summarizes the main tasks that we're doing in this seed funding project. So let me explain one by one. First, this patient-specific model development. We can start with this 3D MRI data. Then we can segment the stomach part, make this smoothed 3D model. And also, we have this time-dependent MRI imaging. There we can extract the motility parameter, like the amplitude and frequency and wave speed. Then we can add that motion on top of this 3D model to make this the physiologically true the stomach model. As you can see, some of these processes can be automated using some AI-powered method. That we are also thinking about that. But now we do have this more physiologically true stomach model. So we started investigating some gastric digestion problems. So one problem we investigated is duodenal gastric reflux problem. Right? So for the healthy transport, the stuff should be transported from the esophagus and stomach and duodenum like this. But if there's some problem, especially on this pylorus, then it may allow this backflow, which is like a reflux of this duodenal stuff into the stomach. Then, as you may know, the duodenal stuff contains some toxic things like a bile and the pancreatic juice. If that enters into the stomach, it can damage on the stomach walls. It can cause this gastritis. Or if this reflux is severe, it can flow all the way back to the esophagus and also cause problem in the esophagus. Right? And there are a number of factors contributing the reflux problems. But the main problem is this pylorus. It's kind of a valve between the stomach and duodenum. For a healthy person, this pylorus should close tightly when the stomach is not emptying. But if there's some problem, it's not completely closed, so it may allow the backflow, which is reflux. But that can be combined with some the emptying problem, like the reduced gastric tone, which is the pressure inside the stomach. If it is reduced, of course, it may allow more reflux. And also this motility problem, this contraction amplitude can be reduced, and it may also allow the more reflux. So again, using our virtual model, we tested the effect of this gastric tone and reduced the contraction amplitude, their effect on this gastric reflux. And this shows the simulation result. This one is reduced the tone, reduced gastric pressure, and this one is reduced the contraction amplitude there. You can clearly see that reduced pressure has more impact on the reflux. So this shows a quantitative result. We found that this rate of reflux flow rate is the highest with this reduced gastric tone, which is gastric pressure. As you know, this gastric pressure is related to the muscle there. Right? So that was a more important factor. And the other thing, we investigate the effect of the food content in the stomach. Right? So the key properties of the food affecting the fluid flow phenomena is, of course, the density and viscosity. And you have found that for this reflux problem, the density has a significant effect. So this scenario, the gastric food content is heavier than the duodenal stuffs. Then it will settle down, so it allows this duodenal stuff refluxing all the way back to the esophagus. But if we do have a lighter food stuffs than the duodenal stuffs, then it can likely suppress the backflow floating all the way to the esophagus. So we have found the significant effect of food property, the density on this reflux stuffs. So the food associated with this category is like juice or wine, and this category is like the olive oil. So, well, it agree with our general sense on knowledge, but it's good to see we can confirm that with the scientific computing. But these are all just with this liquid food, but when also developing this solid food digestion simulation as well. For the solid food, the solid food particles will be layered inside the stomach like this, and there's the enter motion that will make this shuttling motion of the solid food particle. At the same time, the retropulsive jet will make this comminution of the solid food particle, meaning the solid food particle will be the breakdown in the smaller pieces so that it passes through the pylorus. So all these processes are modeled in the simulation, kind of coupled Euler-Lagrangian framework. So the big food particle is reserved by the whole solid body particles, and then we are solving all the 6 degree of freedom motion. But the comminution or the breakdown is modeled by the substitution. So this Lagrangian food particle is dissolved into this Eulerian the stuffs, and then we'll transport it down there. And then this shows the sample simulation result. Yeah, the solid food particle in the watery base, and the solid food particle is the oily based. The key difference is, of course, the viscosity. And you can clearly see the shuttling motion of solid food particle and comminution and eventual emptying to the duodenums. But you can clearly see that this oily based food is digesting slower than this watery based. Again, that in line with our general sense. So yeah, that's that. But again, the most important thing is the validation and verification of our simulation model. So this is like a qualitative comparison with this flow pattern inside the stomach. We can see the flow pattern with the contrast of this imaging. You can see a similar thing here. But this is only a qualitative comparison. So we may want to get more quantitative comparisons. One thing we were able to do is comparison of this sensed pyloric pressure gradient, the pressure difference with the upstream and downstream of pylorus. In some study, they could measure this in vivo, putting this manometer probe through the stomach, and then they measure the pressure, the upstream and downstream. But in the simulation, we can measure that very easily, and we compare that here. Of course, that pressure gradient strongly depends on the food viscosity, so the values are very different by 1 order of magnitude. But at the same time, if we get this in vivo measurement value, so mean value is 0.3, but plus minus 0.2, huge variability. So although this is kind of quantitative comparison, but it may not be critical validation or verification. Again, as I mentioned, it would be great if we can extract like some flow data from this imaging data. In fact, if we look at this contrast, there's a contrast transportation. And if we get the physical equation for the contrast transport, it will look like this. It's time change and spatial change, but that is related to this flow velocity. Meaning this image should contain the information about the flow velocity. In fact, we can rewrite this equation like the inverse problem like this. So we can back out this flow velocity based on the spatial and temporal change of the contrast. But of course, solving this inverse problem is not trivial. So there we can use this data-driven method, like the physics-informed neural network. You can set a neural network, and then we can solve for this velocity and contrast C, and we can use all this automated differentiation and those things. We can put the physical residual and the data rows. And then we can train this the neural network using simulation data where we can clear the answer for the contrast and velocity. And once it's trained enough, now we can put this in vivo imaging data to back out the in vivo flow data from this imaging data. And then we could use this quantitative flow velocity to validate our simulation model. That's one thing, but once this neural networks train enough number of data, we could also use this to directly analyze in vivo imaging data to get better data like the flow velocity in the stomach. So that's the other thing we are actively working on this project. With that, now I can just summarize our e-stomach model. So as I mentioned, it's a patient-specific in-silico model of the human stomach that has all this the simulation capability that can simulate all these digestion problems. And also, we could use this for the portrait surgery. Of course, this resolve as a valuable tool to provide much insight on the biophysics. We can investigate the systematic and regional disorders. And we can also use this for the portrait surgery. But eventually, we can also use this the simulation model to generate lots of data that could be used for the training of the neural network or AI-based method with other applications. So with that, I'll stop here and we'll take some questions.
I thought there was something. Okay.
How important is it to have a patient-specific model? How big are the differences between different people?
Well, yeah, of course, our organs are very different person to person. That's also true for the stomach. There is huge variability in shape and also the motility parameter, like how strong and how fast this contraction motion. So that's the reason why, we want to develop this patient-specific things. We can take not only the morphology but also motility parameter patient-specifics. If it was like 5 years ago, we were just proposing going to simulate all the patient-specific simulation to understand something. But nowadays, it's changing. So once we do have enough data, then we can also train the neural network or AI-based model with our simulation data and also the in vivo data. And that may be used to predict something which was not seen in the data yet, like the different morphology and motility. But yeah, the answer is that there's a huge variability.
Yeah, I was interested on your on a figure that showed, I think, the dissipation as a function of time based on the posture. Yeah. So is it known, or can your models explain how what's the best posture, for example, to lay on if after having a heavy meal, for example, with lots of fat and fiber? Also, is it because there's a break of symmetry? So is it known from the point of view of evolution why that happened? Why is it like this and not like the other side, like the mirror version of it?
Well, evolution side, I'm not sure, but because the human is now it's standing the animal. So, but the first question is, once we do have all this enough information, but input data, we can simulate various things like the aspirin or the different pill and the effect of this posture. That yes, we can do that. Even we can use this like a simulation to develop a better drug design, to accelerate the resolution or delay the resolution, depends on the purpose of the drug. The asymmetry and the other things, the answer is I'm not sure why. So it's out of my scope of the things, but it's interesting. But the other thing we found is that the accelerating the resolution is the reading the right, but after you eating the food, to prevent this reflux, it would be better to lean left. So that's the other thing we have found.
sort of your ground truth? Like, what's your end there? Like, I don't know. I suppose like how many different examples do you have? It's a sequence, right? It's a time series.
Time series, yes.
So, like, yeah, like how many of these things do you have to compare?
So, well, I can tell you that this time-dependent MRI image data is not that many yet, because like kind of the state of art. There are not many imaging facility can do that. So for now, the data we do have is still dozen or 20 or 30, but we hope that we'll get more and more data.
So I was interested in you mentioning training these models on your simulations, and you're applying them to, for example, to reconstruct the flow velocities from actual data.
Yeah.
So your simulations seem really detailed and have a lot of physics in them, but undoubtedly they don't, directly correspond exactly to the imaging data that you get. So how do you solve that problem that the imaging data is going to be out of distribution compared to your simulations?
Right. So for now, we're step by steps. The first thing we wanted to compare is like the flow pattern inside this stomach. So like this. Of course, there's some resolution issue and other the uncertainty issues on the imaging data. But once this neural networks train very well, we hope that. So we can back out this velocity pattern more quantitatively, like the velocity, the strengths, or the size of the jet, or those things that we can compare first against our simulations to get at least the similar velocity magnitude or the size of this jet, or those things. That's first things, but down the road, we may need to compare them more in other metrics as well. But yeah, that's the first step. But even that was very challenging previously, so because there's no way to measure those velocity very accurately in vivo. So, well, that's the first target for us. And then you will see I can tell you that it's not successful yet because we're still working on it. But in the training, the neural network is a bunch of simulation data. It's also take time. So, but we will see at the end of this project how good this approach will be. Thank you.
Well, so it has been suggested that we go ahead and take the break now, and I guess convene in about 15 minutes for the last seed funding. 10? All right, 10.
Our next update will be a seed funding update from Jiafang Song. Jiafang is a fifth-year PhD student in biostatistics at the Johns Hopkins Bloomberg School of Public Health, advised by Dr. Abhirup Datta. Jiafang's research focuses on developing Bayesian inference and machine learning methods for large and complex data sets. Welcome.
Hello, everyone. My name is Jiafang Song. I'm a fifth-year PhD student in biostats from Bloomberg School of Public Health. Today is my great honor to represent our team to share our recent work. And this work is led by my advisor, Dr. Datta, and this is a joint work with Sandy and other collaborators. So the question we share today is focusing on cutting feedback during uncertainty propagation, and we will use neural network and generative models to solve this type of questions. So we will begin with a motivation, which comes from a real-world data set. And we frame this research question into a broad stats problem, which is called cutting feedback. And given the research problem and the limitations on the current methods, we will develop our new method based on the neural networks and sequentially apply on the motivated real-world data set. So in many low and middle income countries, clinical diagnosis of death is not available, especially for child and neonate population. Instead, people will use verbal autopsy, which is a standardized interview of caregivers to collect the information before death, for example, the symptoms for each individual. And those verbal autopsy responses will be put into the AI algorithms so that we can determine the cause of death. And recently, there has been many kind of AI algorithms has been developed. For example, the In-Silico, which is a learned classifiers. And recently, there's a large language model based called Lava. And also there are other type of AI algorithms, for example, using Bayesian inference methods. So given these AI algorithms, we can actually get the outputs, which is the predictive cause of death at the individual level. After we get the individual level cause of death, we can further aggregate them to estimate the cause-specific mortality fractions, which is estimated at the national level. And this estimate is essential to help us understand the disease burden. However, we have used the AI algorithm for a long time, which relies on the assumption that the AI algorithm is unbiased. But this type of way is not perfect. It can cause bias and misclassify the cause. So there's another study which is called CHAMPS program. It performs the minimal invasive tissue sampling for each individual, which we can treat as a gold standard way for diagnosis of death. So paired with the verbal autopsy data, combined, we can learn the confusion matrices, which is contain the information of misclassification risk. For example, on that this matrix, given the gold standard cause of death, we can learn how many will be misclassified to another wrong cause. And here we give an example of a real-world data set. So the off-diagonals shows how many misclassification risks are there. And sometimes it can be even higher than 30%. So this algorithm is not perfect. And recently, Bayesian transfer learning methods, or we call post-prediction inference methods, has been used to utilize what we have learned from this small pair data about the confusion matrices used to calibrate the estimated cost fractions in a more large sample size. So we used what we have learned into the downstream analysis. However, given this pair data coming from a smaller sample size, there will be uncertainty when we estimate the confusion matrices. So instead of giving one single matrix, there will be a bunch of like samples of matrices forming this distribution of the confusion matrices. So how can we passing this uncertainty from the upstream to the downstream is another research question. And oftentimes, people will use a joint Bayesian modeling to model the upstream model and downstream model together, which results in this joint Bayesian posterior distribution showing here. And if we take a deep look at the information flow, we can see for the downstream parameters, it actually has the uncertainty propagation showing here. But for the upstream parameters, we have additional flow from this large noisy data set back to the inference on the upstream parameters, which is not desirable since there are actually no gold standard data information contained here. And this gives us a problem that we want to propagate the uncertainty from upstream to downstream. but we do not want the feedback reverse. So this is called cutting feedback problem, or we can call it cut-based. So there are many situations that the cut-based can be applied or is favored compared with the full-based. So we have seen one scenario is the downstream models are specified. For example, the verbal autopsy example we have shown here. And there can be another example for the air pollution. So suppose we have learned the personal exposure of air pollution, and we have already got some distribution or estimate for this air pollution distribution shown on here. So instead of propagate only one point estimate, for example, the mean estimator into the downstream, we want to propagate this whole distribution in the downstream model. For example, in the downstream model, we can analyze how the air pollution will have the effect on the individual health outcome. But for this downstream analysis, oftentimes there will be a large sample size, but we will use the ambient estimate as the proxy for the air pollution measure, and it will contain measurement error. So it's not scientifically meaningful to use this noisy data set, update the information for our air pollution distribution that we have already learned from the upstream data analysis. So this is example. Another example also can be found in large language models. So given a large unlabeled corpus, we have learned the probabilistic word embeddings. And you can see why it's called probabilistic is given each word, there will be uncertainty distribution around this word. And we can use this probabilistic word embeddings into the downstream analysis. For example, the phenotype classifier given the clinical nodes. However, the clinical nodes may be noisy. For example, they can be typos or copy-paste errors here. So it is not scientifically appropriate we use these clinical nodes to update our upstream posteriors. So those type of just examples for one scenario that downstream models are misspecified. So we may prefer to use cut-based models here. There are other type of scenarios. For example, we have the published upstream quantities showing here. So since they are published, they can be used into many downstreams analysis in parallel, and it's not feasible to update the published upstream samples after each downstream analysis is done. So in that case, it's naturally give us the scenarios for the usage of cut-based. So we can see like cut-based can happen in many different research topics. And in practice, people will just use nested Markov chain Monte Carlo sampling, where the short form is MCMC, to get the cut posterior. Like the idea is given each upstream sample, we will just run a sequentially MCMC to get the density of interest. So, but we can see there's a problem that if we have a very large upstream sample, for example, like 1,000 or 100,000, they can be computationally expensive to run sequential MCMC. Another way to approximate the density is through optimization. So this is an idea from the machine learning thing. So suppose we have some target distribution p theta that we want to estimate, and we have a class of distribution as our candidates. For example, we begin with this red dot. And what we will do is we will optimize this distribution close to target as much as possible. And the optimal solution will be obtained when the distance between those two are minimized. And oftentimes, this distance is measured by the Kullback-Leibler divergence, and we can also call it KL loss. So we get the optimal solution, and we can use that as our approximated distribution. So variational inference has been shown it has contributions into the cut-based models. That is, the cut posterior is actually the solution to a constraint variational optimization. And the constraint is shown here. the right lines indicates the constraints. So the upstream posterior samples remain the same. So that is what we desired as we define the cut-based models. But there are also several challenges for the current variational inference methods. So this method needs to update the first upstream parameters as well. But if there's a data privacy issue, the upstream parameters or the upstream data model is not accessible. So we can now to approximate the upstream parameters. Additionally, this introduced the additional approximation is not necessary, can further introducing errors. And for the downstream, it used a parametric assumption on the distribution. So it used a Gaussian distribution to approximate this conditional distribution. However, only use a Gaussian cannot capture this complex feature as shown in their papers as well. So given all the limitations on the methods, how can we propose a new method to target on the cutting feedback problem? That is our method, which is we call NaviCut. So we design a variational inference methods for cutting feedback using neural networks. First innovation is we will directly utilize what we have learned from the upstream analysis. So the idea is we will integrate all the samples from the upstream to construct our loss function. And we can see the samples as being shown here. And this contains information from the downstream model. And then another innovation is we will use the normalizing flows, which is a generative model. So the idea is we begin with some base distribution Z, which can be easily sampled, for example, standard normal distribution. So our target unknown parameter is theta. So there will exist a function t such that theta is equal to tz. And this t can be a composition of a bunch of transformation, which is invertible and differentiable. So using this neural network, we can construct a more flexible distribution as shown on here. And our method, since we need to use what we have from the upstream, so there will be additional input as shown here. So to get, combine all the things together, we can get this flow-induced density distribution. Based on the previous slide, we have seen that it relies on the universal approximation properties from the neural networks. And in the paper, we also show some theoretical justification of our methods. First, there's a theorem of our proof is that common conditional normalizing flows with a sufficient number of parameters can approximate any reasonable family of conditional distribution. So one thing is that our theorem is now asymptotic. So it given the fixed data set and we do not require any sample size growth. So this theorem can be applied to our methods to ensure that our NaviCut using conditional normalizing flows can approximate both the conditional and marginal posterior arbitrarily well. And more details can be found in our preprint if you're interested in the theorem proof. But here we will give a simulations to show the expressiveness of our NaviCut. First, let's see. So this is the conditional distribution with different numbers of values. So for eta is equal to 0.99, we can see there's a small like notch here. And for those two values, there's a weak multimodal features, but the multimodal features modes will switch with a larger value of eta. And the true conditional distribution is showing on the right dashed lines. And we give out the results for our methods using two type of flows. One is in the green, the other is in the yellow. So no matter how complex the shape is, our methods can align well with the true density function for both the four conditional examples. So combine all the together, we see there's a marginal distribution And no matter which flow types we choose, they can still capture the true distribution pretty well. So this simulations shows the expressiveness of our method Navicat and also give a justification of the theorem. So let's go back to our motivated data set, which is the verbal autopsy calibration. So just recall is that we want to utilize this confusion matrices and passing this uncertainty, this whole distribution together to help calibrate the estimated for cost fractions, but do not want the information flow back. So here comes the results. For each column, it indicates the different causes. So there will be 5 causes in total. And for each row, it indicates different type of AI algorithm we use to get the predicted cause of death individually. And this density shows the estimated cost fractions among the national or populational level. So here is, first let's compare with 2 things, uncalibrated versus full base. Those are the methods, and our a nested MCMC is a gold standard way for compute the cost posterior. As we can see, the uncalibrated and the full base, which is showing on the purple color, I'm not sure if you can see. For example, this is the purple one, and they are quite shifted away from the the gold standard way for compute the cost posterior, which is the orange one. So first, it gives us the sense that we need to calibrate the cost fractions distribution, and also we need to utilize the passing the uncertainty from upstream to downstream, but we need to cut the feedback. Among the methodology, if we compare our Navicat, which is the green color, it's aligned quite well with all the gold standard reference MCMC methods. No matter how complex it is, it's either multimodal or highly skilled distribution, which is consistent with the simulation results. Additionally, we also compare with the parametric cut, where we just use a single Dirichlet distribution to approximate the conditional. However, as we can see, it only gives us some unimodal features, so it cannot capture any complex features showing in this figure. And if we zoom in a little bit to make a pair comparison, so this distance measures how far away each method compare with the gold standard MCMC methods. Clearly, our methods Navicat, showing in the green color, have the smallest distance, which indicates the closest methods that can be achieved to the gold standard MCMC. And in terms of the timing, and our method is 2 to 3 times faster than the MCMC. And also in our paper, we also show that in more complex model settings, our methods can be order of magnitude faster than the MCMC, which gave us a practical use for a large or complex models. So that's it. Some key takeaway is that it is essential to propagate uncertainty from upstream analysis into downstream Bayesian analysis for unbiased inference. And our method proposed is called Navicat, have several advantages. First is ensure modularity, so no need to access to the upstream data model, and we directly utilize symbols without introducing additional approximation error. And also we use this generalized models called normalizing flows, which is do not have parametric assumption on the conditional distribution. And for the theory part, we also show the universal expressiveness for the conditional distributions. And for the application, we just show one example for the verbal autopsy calibration, and propagate uncertainty of confusion matrices will give us a more robust estimated cost fractions. And definitely there will be other wide range of applications, for example, the climate exposure model, and also can be applied into the large language model as well. So we acknowledge the seed funding from the Johns Hopkins University Institute for Data Intensive Engineering and Science, and we also acknowledge other funding support from Gates Foundation. So if you're interested in our paper and methods, please and want to try about our package, please feel free to scan the barcode here. And thank you so much for listening, and I'm happy to take any questions.
We have time for quite a few questions. Are there any questions for Jiafang? All right, I have one. So it seems like there are major public health and public policy implications of this work. How do you turn this into best practices, and then how do you get decision makers to pay attention?
So as we can see, in the real world, we may have a large data set, can be noisy. So we can use a more like small data set. It can be costly to help estimate what we have in the large to help understand the disease burden based on the estimates from a large data set. So in terms of the policy, we can definitely make that into the routine analysis procedure to get a more robust estimates of the causes. So given the more robust causes, we can have the downstream resources allocation to control for different disease and to help decrease the cause fractions or mortality based specific to each cause.
Questions? All right, let's thank Jiafang again. And our next speaker will be Gerard Lemson, the Director of Science for IDEIES. He will be telling us about the Sciserver science platform, which is one of the major principles of IDEIES, one of our major tools that allows you to access data from many different scientific projects and use Python notebooks to analyze and visualize data so that you can do all the work in a web browser, which is great. You don't have to download anything to your computer. You don't have to set anything up. You don't have to download the data. Gerard will tell us a lot more about it.
Yeah, so every year I give a short overview of the status of Sciserver, a science platform. So Sciserver is a science platform that, in Alex's terms, should give interactive access to petabytes of data. So why do you need a platform? We're all doing data science. The amount of data is growing at very high rates, and it requires a lot of expertise to deal with such large data sets. Data is becoming public, it's interesting, and there's lots of use cases to grab data from lots of places, to combine data sets. I'll later say why this is a tricky thing. The data sets are very heterogeneous. You need to be able to deal with different kinds of modalities, as people call them. Science is collaborative, more and more so. We are not all working in 3,000 size collaborations like in certain groups, but still, even with 10, it's already harder to start dealing with it, and you want to share the data with each other. And of course, these days, people want to apply increasingly advanced tools, AI, what have you. So in the old world where you grab data from somewhere, you load it to your local laptop or desktop, and you start analyzing this is going to be a problem. If you want to collaborate, how do you share? You have expertise and experts in different groups. How do they help you deal with your data? So a platform, a single source or a single location where everybody can share the data, where you can share your compute, where you can share your expertise, is actually supposedly it's a solution that we're proposing to this. And so now you can just you put your data in some place. It's somewhere on the web, in the cloud, whatever you want to say. Multiple people can work with it, and so now you can start collaborating more easily. So this is Sciserver. Most people here, I hope, know of it. It's already an old snapshot, but so up there is the link for everybody can register. Everybody can work on this. Doesn't mean that you can see all the data. I'll call about it. So we also call this basically, it's a scalable data integration platform. So you can bring data together, you can integrate it, you can start collaborating with it. And this is because, not because we have some wonderful all-encompassing data model that everything fits in, because such data models don't exist. You will have to do common work. You may have to write code to actually massage your data into forms that can combine 2 or 3 different data sets. However, because you can do this in collaboration, you can share expertise. You can have people who are experts in different data sets, and Sciserver has put a lot of effort on actually doing this sharing and collaboration. So that was a quick background on Sciserver and why. So some updates since last year. For us, the main work as Sciserver engineers, is a few of us here, is that we got a grant a couple of years ago to make Sciserver open source. It was never fully open source. We have shared the code with some people, but NSF gave a grant, a sustainability grant, which is somewhat of a rare thing. Sciserver originally was funded for 5 years during a DIPS project, and then most of the time you're on your own. But we got some extra money and we basically said, to make it sustainable, we need to make it open source, because with our small group of people that are not necessarily paid for this, we cannot keep sustaining it. We cannot just keep growing it. And so now we know of all these people out there, as Eric says, chomping at the bits to start adding features to Sciserver. That can now be done because Sciserver is actually now open source. There's some other steps that we're going to do. This is our Gantt chart. Not quite done. We have a no-cost extension, because why not? But so it's now public. There's an open source. So everybody can download it and deploy it. It's really public. You might not have been able to read it up there. So this was not enough, of course. We could have from the beginning said, okay, we put it all in one GitHub repo, switch to public. There's a lot of work that is still ongoing, documenting it, code cleanup, and all of these kind of things. So anyway, it's there. If people want to download it and want to start working with it, if you have a Kubernetes cluster, you should be able to do so. So this is, anybody can run Sciserver now, even without our help, supposedly. But we have our Sciserver instance here at Hopkins, at IDIES, since 2017, roughly, it has been running. So there's some extensions that we've made recently. So I'll just make in this last year. We've been working hard on transforming our data center storage capabilities from Datascope nodes to Ceph clusters. So Ceph is this sort of file format. So a second one is now available. So now in total we have 20 terabytes available. This is not all for Sciserver. Also, some of the projects that I'll mention shortly are using it. We have a large compute cluster. In principle, should be 25 quad nodes. Because I think of cooling constraints mainly, we cannot turn it all on completely. But so each node has 128 cores and 1 terabyte of RAM. So 100 of those will give quite some compute capabilities. All CPU. We have GPUs, not that many yet. SSEC bought 16 A100s. We have, I think, a few Grace Hopper nodes. I don't know. Again, cooling. So some work that Dimitri there has been working on is to make Ceph available. This is a technical term for user volumes. And we've created new compute images. So when you run in Sciserver, you generally start a container, a Docker container based on a certain image. Most of the time it runs Jupyter. So it looks like Jupyter Lab, as you would have on your laptop. This is something that we've supported from the beginning. You can also run RStudio for people who want to run R. And they come with libraries pre-installed, like the typical Jupyter Lab image will also have, say, TensorFlow and PyTorch, as well as scikit-learn and Pandas and NumPy. New one is VS Code. So lots of people like to use Visual Studio Code for debugging and everything. You can run that now on Sciserver directly. There's a web version of it. It's in test. If people we haven't made it public to the world yet. If people are interested, let us know. Maybe we'll just make it public. But then we ask for people to give us feedback to this. No, this was something that we just set up in an afternoon. Sure, I don't know. Something like that. And but it's not complete, it's not comprehensive. So something that we have to do. Another thing that we also do is we give people desktop environments. Again, not yet public because we just thought it's almost too powerful. We just have a desktop running on our data center. And you can run desktop things in there like a browser or MATLAB. So we have a MATLAB license. What is it? Can't think of the term right now. Anyway, but it's completely free to use. It's just up to us. Now it's a campus license, so it's up to us if we want to allow you to spend our CPU on that. So it's just the desktop version of MATLAB running on this desktop. This desktop we can also customize. This is things Maggie gave me this slide. It's of the tool from her project, Coda, this Nippani desktop tool. It requires GPU, so the configuration is not trivial. But in principle now you would have a tool that you can share with your collaborators within a group maybe. We don't give the whole world access to our GPUs. We've had problems with crypto miners on the CPUs only enough already to allow that. But so we can customize these things like that as well. So there's a lot of freedom and a lot of power that we can give you, and it's all running on our hardware. So those were just features of our Sciserver instance. So some new projects that we support. So we're supporting, as Alex showed, his diagram, or the bubble diagram was already somewhat out of date. Each of the big blue boxes are disciplines. These green ones are things that are institutes that we support, like DSAI and SECC. All the other ones are projects that we support, have supported, are supporting. The yellow ones actually provide an income stream to us, some way or another. And so this is growing continuously. But so there's a bunch of user scenarios here. So it's education, and I'll show a couple of these. I'll really skip over them quickly. If you have interest in learning more about them, ask me later, because I've got way too many slides, obviously, but it's just to give an overview. So Sciserver is very useful for education. Fred Tan there has worked on a project, Seymour, where they created a curriculum for genomics, bioinformatics. I don't know all the details. Together with J1 from our team. And this is used for community colleges, for example. Because everybody can register, somebody needs to create a curriculum, and now you can share it easily. And that's easy for them to use it on our Sciserver, then that everybody spins up their own. That is going to be hard. So for more questions, for more information, ask Fred, for example. As Alex already mentioned, we've been working with the Turbulence group for many years already. They added some new data sets, and these are now also more easily accessible directly from within Sciserver. Mike Snowbold sitting there, he wrote a new tool called Nippani for accessing data in ZAR format. So we have now probably one of the largest hybrid simulations ever. It's about, for one time step, it's 0.5 petabyte. We have one time step. So there's also some and this is really cool. I hope it works. The simulation, hydro simulation of turbulent flow around wind turbines. So this is So all this data is available on Sciserver for free. Ask Mike how to use the library. A project that I started or that I helped with. So this is this concept of sharing expertise, and I think this is one of the more. It's sharing data everybody understands, but you can actually start sharing expertise. It's important. I don't know anything about perovskites. Don't really know what they are. Paulette does. He has a student who has run simulations of what happens if one of these things is hit by a cosmic ray. This might happen if you use them as solar panels in space. Apparently, they seem to not be suffering much damage, so maybe they repair themselves. So they have simulations there. So the data of these simulations was not that large, like 16 gigabytes. We could store it on Sciserver, massage it into a different format, Parquet, which is way easier to use using DuckDB, which is basically you create a database, a relational database for yourself. So you can run queries. This shows we create a crystal, all kinds of different atoms. This is how we move in time. This is what I recently got from Gerard paper. This is where the particle hit and then after a certain time how much damage, how much the structure has been caused. Okay, I'll skip up. So there's been a new SDR19 as for the Sloan Digital Sky Survey. This you can read about this also in the annual review. We've started downloading lots of other astronomy data sets, Manu in particular. Dsai, we have 300 terabytes of that. Some of the people here have already started analyzing this on Sciserver. We hope to start gathering more astronomical data sets. We have simulated simulations as well. A project that we have at Agora, which is, I think, there are buildings being opened as we speak, they're interested in democracy. And so we are downloading data for them, putting in a database, make it easily accessible, etc. I won't say much about AM-Bench, a project that Bailey J1 and I are working on with NIST. NIST is currently in a shutdown, so we can't work with them. So very quickly, if I may overrun, maybe people should not ask questions now, but they can ask me questions afterwards, so it will be 3 more minutes. So we support SSCC and DSAI, first of all, by allowing them space in our building. In the hallway, we've had to compress ourselves. We think that we thought that in January we would have to move to Mount Washington. May now be March or later, we don't know. We'll see how that's going to go. We're supporting some project, as Edward already told. So for SSCC, we do segmentation of neural dendrites. We support this on Sciserver. They could run, this is with Ryan and Vlad, who is not here right now, but run a UNet training on Sciserver using the GPU cluster that we have. We're supporting a project with Abhi et al. For air quality, and so there are sensors all over, not all, but somewhat localized places in Baltimore. So there we can create, with their techniques, they can predict what the air condition is in places that they don't look at. Sciserver helps here that you can very easily create notebooks that actually go and look at the data for prototyping. Okay, because there's one thing that I definitely want to say. So soon we'll go to that building, somewhere in Mount Washington. It looks fancy, but we'll see. I want to thank our people in our team. These are the names. Some people are no longer formally in IDEIES, but they've still been helping with this. The one thing that I want to mention is that we were very saddened that early this year, Ying Dai, who was a junior database administrator with us, passed away after a long fight with cancer. She left 2 young kids and a husband here. So we still miss her. She was a lovely person. And these things happen as well. It's not all fun. Thank you.
We have time for 1 or 2 questions for Gerard. Any questions? Yes, I'll bring you a microphone.
It's great that there are all these data sets that are already there and that more will be arriving. Some data sets are already large and that they're being hosted elsewhere and would like to work with them. Some collaborations may already have supercomputing allocations on national centers, but might want to use this infrastructure. Do you have any cases where people have used Sciserver on, let's say, access facilities to work with data sets that are available there locally?
You mean that people work on our Sciserver instance with remote data sets?
For example, or what are the, I'm asking a general question, what are the modalities of using this infrastructure for data sets that are not necessarily hosted here? Yeah. And with compute that may also be elsewhere. Is there a possibility for doing that?
One thing that we've been thinking of is not for such a large, but say at March. Soon we will hopefully get Weka as a file system over across campus, and so that there could be a larger compute system like Rockfish having access at our data here automatically. Other things that we have done is, for example, the Poseidon simulation data set. We did get here efficiently using, say, the open storage network. So those could potentially be ways of doing it. Bringing our data, and the thing of Sciserver is bring compute to the data rather than the data to compute. Sorry. And so we are not a supercomputing center, indeed. Though soon we may have loads of these little computers of Alex, and would become one, but maybe Alex has an idea.
From NERSC, we moved over a petabyte of simulations, or the 4 petabytes of ocean circulation model was done at NASA Ames. So the model is that we actually use typically the OSN open storage network nodes to actually move massive amounts of data, because there we can move about a petabyte a day with that. So we can move things at wire speed at 100 gigs. So, because otherwise, so if the data is somewhere else and the compute is somewhere else, okay, so why run then the Jupyter notebook at Hopkins? So then we might as well, you might as well want to run the skin there. So, because bringing the data dynamically here to do the compute again to somewhere else, that's not a very efficient way of tackling. So whole point in doing these computations is to have the data located right at the same place on a very high-speed network as where the data is. And there we are switching. So in the computer room now we have 100 connections, but we're switching over to 400 between the data and the compute.
It's just being because there's seems like there's additional value in this in the server infrastructure, which enables collaboration, and so where often national facilities are already used as places where collaborations work on common data sets and use the compute there, but the software could potentially be useful in that context as well, given that it's open.
One thing that a point that Alex made, and that I have somewhat copied there, is lots of the work that you want to do is interactive. You want to explore before you maybe develop some of your code, try it out before you then submit your large job that you run. And so for the interactivity, we're well placed. The large jobs could be pushed to Arch. We've thought in the past about, okay, if you have the money to use your AWS account and push data up there, that might not be the full petabyte. It might be the subset of the data that you want to analyze. So those are the kind of things that we would like to explore because, I mean, it is true. I've seen it in the past. With the Millennium XXL simulation, it was so large to analyze it. You needed a supercomputer, and therefore there was way less use of that data set than the somewhat smaller ones. Mm.
Is installed within Brookhaven National Laboratory and then the Max Planck Institute to serve eRosita for Max Planck, and within BNL. BNL case is not public, but it's for users within a division of Brookhaven, and they make available like a cluster of GPUs for their work and collaboration over that. So it's not exactly a national facility access at that level, but it's used basically to facilitate access to their internal facilities. So that kind of use case is happening. And ideally with the open source system, maybe it can happen more for those kind of facilities that don't have the answer already.
Thank you. Let's thank Gerard. Let's thank Gerard again. All right, now we will hear updates on the 2025 IDEAS Summer Student Fellowship Program. The Summer Student Fellowship Program invited Hopkins students to apply for a 10-week summer research program, and we'll hear from each one of them today. First speaker will be Alex Larson.
Hello, everybody. My name is Alex. I'm a senior here at Hopkins, majoring in applied math, and I am one of the 4 recipients of this past summer's IDIES Student Fellowship. I'm very excited to be here today with all of you. So my project this summer, titled AI-Driven Cardiac Telemetry Classification for Afib Detection. So let's start with the cardiac telemetry aspect of this. So some of you may be familiar with the electrocardiogram, the ECG, which is the test that, so you can see here at the bottom left, kind of what it looks like. It's what physicians will look at to monitor the heart rate and heart rhythm of patients that are being kept in the ICU. Cardiac telemetry is just the longer generalization of this, spanning, it could be days, weeks, the entire patient's stay in the ICU. So it is the most frequently collected data for ICU patients, and it's especially important because the heart modulates the rest of the body, and this really stresses the importance of researching and analyzing this telemetry. So atrial fibrillation, or AFib, is the most commonly sustained arrhythmia and affects millions of people worldwide. It can increase the risk of stroke, cardiac arrest, and potentially other severe conditions. And missing it can have real consequences. So it's very important that we detect this early because early detection enables early intervention. Moving on to the AI-driven aspect of this. So typically, when it comes to these cardiac telemetries, physicians will go through and denote atrial fibrillations by hand. So as you can see, like this can be very tedious and inefficient because physicians are looking at weeks worth of data for hundreds of patients. And we want to try to use AI, specifically neural networks in this case, to improve this efficiency and speed of the process. So we're utilizing a neural network to classify the telemetries of patients in the Johns Hopkins Hospital Neurosciences Critical Care Unit, the NCCU. And we find that this network model we use is very accurate and has very high recall. Basically that it minimizes the missed AFib episodes, which would be very bad to say the least, I suppose. We also find that it can be used to successfully do this, and I'll talk a little bit more about specifics on my poster if you guys would like to stop by later. So going forward, the future of this project, we want to try to connect these AFib episodes to its effects on other parts of the body. For example, so when AFib occurs, the rest of the body's processes are likely affected, and we want to try to understand and try to quantify the effect. For example, ICP, intracranial pressure, is another large area of research in our group, and this is just one of many areas that we'd like to delve into in the future. And finally, I'd like to thank Kate and the rest of IDIES for this opportunity. It really enabled me to do research in a group with other like-minded people this summer, ranging from physicians at Johns Hopkins Hospital, professors through multiple schools, such as Dr. Budavari, who's here today, and PhD students, to work on some very important real-world research. Overall, I think it was a great and very valuable experience to be able to do this in a product that I really enjoyed. Thought was very helpful for my academic career. Thank you.
Thank you, Alex. Are there questions for Alex?
You mentioned you use the neural network for the detections. There are many kind of different architectures of the neural network. How do you decide which architecture to use?
So we used a pre-trained residual 1D neural network, and then we had to kind of accommodate this neural network. This was pre-trained on other ECG data, and we had to accommodate this network to align with the data that is collected at the NCCU.
Yes, I'll bring you a microphone.
I'm just curious, for this sort of data, who decides what the ground truth actually is in order to do the training?
That would be the physicians that tediously go through and analyze these signals.
Right. Is that signal analysis checked for consistency, accuracy, other things like that?
Yes. So multiple physicians will do the same annotations and will cross-check to see if they have consistent findings.
I see. And is there any way to determine whether or not they don't do the most perfect job and are missing anything from sort of just going through this process of training and then feedback and whatnot?
I mean, and so are you talking about the physicians?
Yeah, I'm talking about basically just human error and bias that is almost certainly in that.
Certainly.
Yes. And how one deals with that, and if the process of doing this training and feeding it back tells you anything about what that bias might look like and or what the error rate is.
Okay. So I guess one specific example I'll use in terms of just the human error is there'll be instances where a patient will kind of fluctuate in and out of AFib over like a several minute period. And so let's say they have like a 5-minute AFib interval followed by like a 1-minute normal back to AFib. So sometimes physicians will kind of just group this entire thing together. And if this happens like multiple short normal segments, the entire batch will be just labeled as AFib. The neural network actually does a pretty good job of catching this in terms of like finding those little normal segments in between. So we're hoping that this neural network is able to identify the potential human errors.
Okay, thanks.
There's time for one more question for Alex.
have you compared this with more traditional time series analysis methods? I'm assuming that people have been doing this before, and I don't know what I'm not an expert on the techniques, but how does it compare to, say, AI-driven, so data-driven analysis?
This is one of the state-of-the-art models that we're using for ECG classification.
All right, let's thank Alex again. And our next student fellowship speaker will be Srisha Nippani.
Hi, everybody. My name is Sri, and over the past few months, I've been working with Professor Maggioni from the Math and AMS department to examine the dynamics of agent-based systems. So just to use an example, consider a predator-prey system. And I have a GIF for you guys. So on the left, you have observed data, and on the right, you have a prediction from a learning algorithm. So I'll just play it again, and as you can see, it's pretty good, right? So now, of course, this is not just a one-off example. Systems of interacting agents are ubiquitous in nature. Of course, we have predator-prey systems. We also have opinion dynamics and consensus formation on social networks. We have birds that flock in a certain way. We have phototaxis of bacteria, so on and so forth. And agents in these examples could be people, atoms, animals, cells, so on and so forth. So this alludes to some universal problem, right? So given observations of the trajectories of a dynamical system of interacting agents, how can we learn the interaction rules? That is the main problem that we are trying to answer. And typically, in such systems, agents have states which evolve over time by interacting with one another. And we can interpret, and they interact based on some underlying structure of or geometry of the space they exist in. And we can interpret interaction rules as a system of ODEs or PDEs, or in our case, a system of stochastic differential equations. So this equation just means that the change in state of an agent is some weighted average of the interactions with other agents. That's pretty intuitive, and it's a pretty reasonable assumption to make. So the interaction kernel basically tells you it tells you the rules of the interaction, and the network in which these agents exist in are represented by a matrix, A. So the matrix basically tells you whether two agents interact at all and how strong the interactions are, and the interaction kernel phi tells you the specific rules governing the interaction. So now our objective is to jointly estimate the network and the interaction kernel. And of course, I would like to convince you that this is not a trivial problem because this is nonlinear, right? The system is nonlinear, and there are some techniques that we have developed. The first one is to do an alternating least squares method. And this is justified by the fact that this model is quadratic with respect to the parameters. And so if we fix the kernel it is linear with respect to A, and if you fix A, it's linear with respect to C. And so the alternating least squares algorithm basically bounces back and forth between the network and the kernel, and it converges to some result. Another technique that we looked at is that is more novel. That is, we called it operator regression followed by an alternating least squares. Basically, we treat we consider the product matrices of A and we consider the product matrices of the network and the kernel. Basically, the kernel can be thought of as a coefficient vector corresponding to some hypothesis space of functions. So we jointly we consider both the network and the kernel as a single operator, and we do a regression to estimate the operator, and then we do a simple factorization to get the network and the kernel. So this was the framework developed by Professor Maggiani, and this solves one instance of the problem, right? Because here we're assuming that we have a system of agents that interact in a pairwise fashion. So two agents interact at a time. But of course, in various phenomena that occurs in nature, we have higher order interactions. And that is really the goal of the work that I've been doing over the past few months, to generalize this to higher order interactions. And this makes the estimation algorithm more challenging because the regression matrices are more ill-conditioned, and you have more parameters, and naturally it is harder to estimate the parameters, right? So I'm happy to talk to you about more specific details of the project later during the poster presentation, and I'm happy to answer any questions. Thank you.
Thank you. Are there questions for Sri? Yes, we'll go there and then here.
Thanks. So I was just wondering, the rules themselves, are you interested in getting what one would call simple rules, or can the rules be as complex as the system is, or does it matter to what you're aiming for? And simple meaning, I guess, fewer independent parameters.
Yeah, so I guess if you mean by simple rules like a qualitative description, I guess, no, that's not what. Okay. Oh, well, yes. So, I mean, the rules are just, the rules can be thought of as a system of ODEs, right? So, for instance, if, it is natural to assume in this case that if agents interact, the change in state of an agent is some combination of its interactions with every other agent. So that leads to this very natural system of stochastic differential equations. So if we are able to estimate the underlying network or geometry of the space, meaning what agents interact with what agents, right? We have to figure that out. That is encoded by A. And if we figure out what the function phi is, which encodes the functional rules of the interaction, then we have basically, come up with a system of, we have fully determined a system of stochastic differential equations, and that is the rule of the interaction. And the whole point was that this is going to be a model that is application agnostic, because much of the existing literature focuses on specific problems like, predator-prey relationships or birds flocking, right? But this kind of models any kind of interaction. I hope that answered, sort of. Okay, thank you.
Estomach, you already partially answered my question in your previous comments. I was wondering, for a general function phi, how do you distinguish between, can you actually separate out A from phi?
Yes. So for the pairwise case, so now we're assuming at any point of time at most two agents interact with each other. So in a second order setting, you have this system, and both algorithms, ALS and orals, they both estimate separately the network A and the kernel phi. And for orals, there are actually theoretical guarantees, although for ALS, there aren't. So that is an issue right now. But our heuristics would suggest that ALS does work, and it actually works better than orals, which is interesting. And I mean, we have some guesses as to why that is the case. I'm happy to share it with you later. But right now, my work over the summer has been trying to extend this to ternary interactions, and we've made progress on that. But we're going with an alternating least squares approach for ternary order interactions, and yeah.
Just a quick follow-up. Do you assume symmetry, for example, in phi?
No, there's no symmetry. No specific structure of phi is assumed. But we do assume that phi exists in some hypothesis space. So it's a parametric estimation. Yeah.
Hi, thank you so much. So I wonder if you're aware of the work by Professor Venkata Subramanian at Columbia. He's used a combination of statistical mechanics and game theory to look at these kinds of phenomena, birds flocking, anthills, and so on.
No, I'm unfortunately not familiar with the specific work you're referring to. So do you mean that those models are general, or are they like application specific?
They're not application specific.
Oh, okay.
It's a whole general area. I just think if you haven't done it, you might want to just check in and see other ways of looking at the same problem.
Good to know. Thank you.
And he's an AI expert, so.
Nice.
Let's thank Sri again. Now our next student fellowship update will be from Ju-Young Ryu.
Hello, everyone. Sorry for the delay. Hello, my name is Stu Young, and I am a fourth-year undergraduate student here at Johns Hopkins studying computer science. And my project is called AI-driven. Sorry. This project was under the guidance of Dr. Robert Stevens and my lab called LCICM, which is a lab that focuses on computational intensive care medicine. So a quick introduction, stress cardiomyopathy is an acute cardiac dysfunction. It's also reversible and underdiagnosed, and is a pretty rare disease. Around 1% and 2% of all ICU admitted patients have this disease. Another reason why it's called stress cardiomyopathy is because it is very unique that it is known to be triggered by a recent physical or psychological stress, such as a recent car accident, recent surgery, or loss of a loved one, which is why it's called also broken heart syndrome. The problem with SCM currently in the clinical setting is that the clinical presentation of SCM closely resembles acute myocardial infarction, which is also called AMI or heart attack, leading to frequent diagnosis and inaccurate treatment decisions in the ICU. In a recent study, around 7% of all AMI patients were actually identified to be SCM patients, reiterating the difficulty in the clinical setting to differentiate between these two diseases. There has been previous work using echocardiograms and using deep learning in order to differentiate between SCM and AMI. Echocardiograms are cardiac ultrasound videos. And however, they were able to achieve moderate accuracy of AURC of 0.8. However, they have some limitations they are only limited to certain view types of apical 2 and apical 4C, Apical 4-chamber view types. What I mean by view types is that echocardiogram, these ultrasound videos are collected by using a probe, ultrasound probe on your heart, and it basically has different orientations, angles, and zooms of your heart. And A2C and A4C are one of the standardized views that are widely used. Also, previous work lacked EHR integration and also external validation data sets under severe class imbalance. So this project was made, the main aim for this project was to build a multimodal machine learning model that integrates both echocardiograms and clinical features from the EHR to differentiate between SCM from AMI. So the data set that we use is called MIMIC4, which is a publicly available data set from PhysioNet and collected by the Beth Israel Medical Center in Boston. We have identified around 33 SCM patients and 560 AMI patients that had echocardiograms that were collected within the ICU. You can see in the bottom left here is the modeling scheme here. For the echocardiogram model, we use ResNet as well as attention layer, which produces a 512 dimension embedding, and then an XGBoost model was used for the final classifier. For the EHR model, we identified around 45 clinical features, including age, gender, medical history, medication administrations, etc. And then we also used the XGBoost classifier. For the fusion model, we concatenated the 512 embeddings and with the 45 clinical features for the final classifier as well. You can see that for the results, the echo model significantly outperforms the baseline AUPRC, which is around 0.06, which is the positive prevalence within the model. Also, you can see that the fusion model outperforms the two unimodal models, the echo model and the EHR model, showing that both modalities, the echocardiogram and the clinical features, work synergistically to boost predictive performance of the model. Some strengths of this model is that it is the first study to incorporate all echocardiogram view types, not only limited to A2C or A4C types, but it can also it also performs very well on short videos such as less than 10 or 15 seconds, and also non-standardized clips. It also explores and shows the potential of integrating these EHR features and the potential of multimodal modeling under these highly imbalanced clinical data sets. Some limitations is that the SCM sample, as I mentioned, we only have 33 SCM patients within the cohort, and around 60 echo studies, which means that for five-fold cross-validation, we have less than 15 echo studies per test fold. And we had to validate that through the cross-validation process. We also had a lack of clinical features. Like I mentioned, stress cardiomyopathy is unique that it has a recent stressor feature, whether physical or psychological. However, within our data set, we lacked that clinical feature, as well as other cardiac biomarkers to use within the clinical data set. Some next steps is to expand this model and evaluate our model on an external validation cohort. We're currently in the process of acquiring echocardiogram data set from the Johns Hopkins Hospital, working with the cardiology department and using the PMAP platform for the clinical variables. We also plan to incorporate explainability tools such as GradCam or SHAP to identify key visual features and clinical predictors for the final model prediction. Thank you for listening, and I also thank IDIES for this opportunity. Thank you.
Questions for Jiyoung?
Thank you. That's a really, really interesting clinical application. But when it comes to a clinical setting, even ensemble models, sometimes clinicians and patients would be really hesitant to accept them because they don't know why they're coming up to that answer. So as predictive models, they could potentially be powerful, but as hypothesis generating models, they're even more powerful. And so you had 45 clinical features. You did say that you're interested in using like maybe some Shapley analysis to explain individual predictions, but did you happen to take a really quick look at variable importance? It's really easy to extract from the model, just like see what the top 3 top features were.
Yeah, so in terms of the EHR clinical in terms of the EHR model that only uses the 45 clinical features, the leading clinical factor was actually gender or sex, because actually SCM, around 70% or 80% of SCM patients actually are postmenopausal women. So that was the leading clinical factor there, as well as comorbidities such as hypertension or diabetes. Those were the main leading clinical factors affecting the model.
Interesting. Thank you.
Thank you.
Questions? All right, let's thank Jiafang again.
Thank you.
And our final student update speaker will be, I have to check the thing. I forgot your name, sorry. James Dieva Boshane? I got it. All right. Thank you.
Great. So I would just like to note, so I don't have any names up here, which might be a key error, but this work was done under the supervision of Brice Menard, who's in the physics department. He provided a lot of invaluable support throughout this process that really helped underlie some of the results that I'll discuss here. So I spent the summer looking at this algorithm, the deep image prior. So it was introduced in 2017, and it uses neural networks to do like basic image inverse tasks. So the one that we're really interested here is in painting. So the problem is you give the network this corrupted image where parts of the image have been obscured, and you ask the network to fill that in. So I would just note that the core aspect of this process is the network has to have some kind of fundamental understanding about the essence of what the image is, and therefore it's kind of implied that it has some understanding about the distribution of natural images. So on the top row above, you're seeing an example from the original paper, and you can see this is a reasonable guess as what might be in the blank areas. But the really interesting piece of this algorithm is that the network used for this has not been trained on a large data set of natural images. In fact, the network has only ever seen the image to the left. So this is really astonishing. Some of our most fundamental assumptions about deep learning is that it requires these massive data sets and many, many samples in order to estimate sometimes billions of parameters that are included in the model. But here we're seeing that's not the case. So there have been many, many papers in the literature trying to explain this phenomena. And my project over the summer was to try to take a weights-based perspective to this and study the weights of these networks to try to understand what the core essence of this process was and what it might be able to tell us about neural networks as a whole. So in our group, we try to understand principled ways to analyze and understand neural networks. So in particular, Brice and some of his collaborators have come up with kind of an interesting way to view the weights of networks that leads to natural notions of what a feature is for the model, like an effective dimensionality of the encodings of a network, and understanding kind of, and being able to, in a principled way, probe what the network is doing internally. So I extended this analysis and applied it to the deep image prior. So I would say the core of the result is that the process that the network is doing, or its fundamental mechanism, is low dimensional compared to the capacity of the network. So I'll just say broadly, you can think of the plot on the left as indexing features at a given layer, and the larger the value, the more important it is to the network. But we can kind of pull out two regimes across every layer, where we're calling regime A the lower ranks, where in in this log-log plot, you're seeing kind of a more exponential curve. And then regime B is kind of the high rank power law that you're seeing at the end. So by probing what these features are doing, you can understand that regime A is encoding kind of low frequency features in image space. So things like, if you're looking at this image of the truck below, like the fender in front might be like some wave that's being pulled out from one of these components, or things of that nature. Well, regime B is encoding essentially high frequency details in the image, things that do not correlate spatially beyond, very hyperlocal regions in the image. So what's interesting about this is you can see this, I would reemphasize this plot is in log scaled on the x-axis, but regime B is dominating the dimensionality of the network. Right? Most of the features that the network has are going towards filling in all the details. However, it's regime A that's really the fundamental piece of understanding what the image is. And again, we're measuring understanding of the image as the ability to inpaint, right? The ability to generalize on what it's seeing. So these sets of 4 images that you see on the bottom are some experiments that we've done. On the left is the masked version, the corrupted version. The middle column is what the network has inpainted. And then on the right, what you're seeing is when we restrict the network to only use the features that we're saying belong to regime A. And what you can see is the network is capturing essentially up to our perception, the full essence of what the image is, only with up to about like a quarter at a maximum of the total capacity it has access to. And secondarily, the spaces that are being inpainted are also, their representations are dominated by regime A internally in the network. So this is kind of where we're coming to the conclusion that there's some low dimensional structure within the network that's responsible for this understanding of what the image is, but then most of the network's features are going towards filling in the details, which is interesting within itself. And you can see these two regimes occur from a lot of different perspectives you can take on the weight structure. So there's a little more than I'm alluding to here. But kind of finally, so this could have a lot of implications. For example, like how we view image, like a measure of image complexity. Like natural images, it's kind of hard to say from a network's perspective what's complex and what's not. But looking at the encodings, we might be able to puzzle something out. But another direction we're actually considering is, does the brain do a similar process? So just as a very rudimentary thought experiment, right? When you see something, you're seeing it in all of its detail, right? But then close your eyes, and I would say for the most part, you're just seeing some kind of essence of what you were just looking at. You might say like an approximation of it. So is there some internal mechanism in the brain that's having this kind of dual behavior? In memory, you're seeing some kind of compression. So this is kind of an open question we're considering next. We haven't fleshed out that much. But so thank you to IDIES for doing the fellowship. It was a great opportunity. I feel like I've learned a lot. And, so if anyone has any questions.
Questions for James? Yes, I'll be right there with a microphone.
So just in the implementation of this, is it always like a unique restored image that comes out at the same level of reliability, or does it sometimes gives you an option of a few that you would need to choose between?
So I didn't have time to go into the specifics of the algorithm, but what it does is you're mapping a fixed random tensor into image space, and then you're updating the weights with just a simple loss function of what the image is. So you're just reconstructing one image that you can sample across random initializations of the network. And sometimes there's a little variability just in the optimization process and other factors, but per run, you're getting one unit.
Other questions? All right, let's thank James again.
Thanks for a great talk. Very pleased to introduce our next keynote speaker, Beth Willman. Dr. Willman is the CEO of the LSST Discovery Alliance, the organization aiming to ensure that any scientist with an excellent question for Rubin Observatory's LSST has access to the resources needed to answer it. She discovered the first known ultra-faint dwarf galaxies, including Willman 1, now known to be the most common type of galaxy in the universe. So let's all welcome her for a really exciting keynote talk. Thank you.
No. Thanks. Perfect. Okay, great. Thank you. Hi, everybody. I'm so glad to be here today. Thank you so much, Alex, for the invitation. I'm going to spend my keynote talk telling you about the Rubin Observatory and the imminent start of the Legacy Survey of Space and Time. I'm going to tell you how the technical marvel of this astrophysics experiment, plus the openness of the data, plus the community-centered design, really create a staggering opportunity for discovery, the potential to democratize astronomy, democratize STEM, and set examples that other data-intensive fields can learn from. I'll spend the last bit of my talk highlighting the fact that despite the fact that this staggering opportunity is being produced, there's also the possibility that there'll be an increasing divide between scientists and institutions that are able to seize this opportunity and people at scientific institutions that don't have the resources needed to fully take advantage of this large and complex and high velocity data set. And just give a couple of examples of the things that people are doing now to put discovery in the hands of the brilliance that you can find at a wide range of places, not just those with resources. And so I want to start with the naming of this facility, which is the only major scientific facility, at least in the United States, that is named after an astronomical facility that's named after a woman. And so Vera C. Rubin, who is now deceased, she is a well-known cosmic trailblazer in our field. And so her work provided the first convincing evidence for dark matter. And she did this with innovative approaches to using the most cutting-edge technology of the day. And so she's known both for revolutionary discovery, innovative use of cutting-edge tech, and for her support and advocacy for individuals that might not otherwise have had the opportunities that she'd have fight really hard to get in the field of astronomy. And anyone in the room who's an astronomer has heard many stories coming from Vera Rubin in her day, everything from, going to the observatory to observe, and there was no women's room. And so instead of just not going to the bathroom, she drew a stick figure wearing a skirt and taped it to the door and then used the restroom as she saw fit. And so during the first Trump administration, the NSF DOE Vera C. Rubin Observatory received its current name by an act of US Congress in December 2019. So starting with the technical marvel of this facility. So cutting edge technology for a new era. These three components, starting with the LSST camera funded by the Department of Energy and built at Ssec. This is in the Guinness Book of World Records for being the world's largest digital camera. Also, I believe having the world's largest lens embedded in it. 3.2 billion pixels are in this camera. It had its own chartered 747, flying it from California down to Santiago, then getting driven across Chile and driven up the mountaintop. Those 3.2 billion pixels are read off of that camera in 2 seconds. So at every layer of this facility, there's a new technical marvel that goes into how it can do what it does. This 3.2 megapixel camera on the Simone Survey telescope with a unique optical design, allows this experiment to map the sky more rapidly than any facility previously built. And so there's a novel, it's 3-mirror design. The primary mirror has the tertiary mirror embedded within it. And so on this 8-meter class telescope has a nearly 10 square degree field of view. And so that's about 45 full moons. And just the way human bodies are proportioned, if you hold your arm out like this, your thumbnail is a really good estimate of the size of a full moon. So you can imagine what this is like in practice. You've got about 45 of your thumbnails with every image, 3.2 billion pixels, every 40 seconds, every night for 10 years. And when we say Rubin Observatory, it's not just that beautiful building on the summit. It is a whole system. It's a global data management system that's not just in the US, but also in the France and the UK to manage the 20 terabytes a night of data. So when thinking about the new challenges, I'm a child of the Sloan Digital Sky Survey era. It feels good coming home to one of the primary birthplaces of SDSS innovation in the earliest days until now. In that time, I could look at any image I wanted on my computer. I could download all the stars onto my computer, write terribly written code, and get some really interesting analyses out. Now, a single image requires 400 Ultra HD TV screens to display it. The human eye can't even look at a single image and conceive of it all in your brain at one time. And again, every 40 seconds, every night, for 10 years, in 6 different filters. So this experiment will get a color images, information as well as position, and changes with time. And so combining the unique optical model, which gives us a wide field of view, with the properties of the camera, scanning the sky for 10 years is going to generate the greatest cosmic movie of all time. So we won't just have static images, and I'll say a bit about what sorts of data products scientists will use, science-ready data products scientists will use, but we'll see how the sky is changing with time. And one of the reasons this is so impactful is that LSST, even though it was first thought of in the late 90s as the dark matter telescope, that's what it was called, going into the 2000 Decadal Survey of Astronomy. The technical design of the telescope was based on 4 different pillars, galaxies, stars, the changing universe, dark matter, solar system. I listed 5, but you can combine them and make it 4. It's not because this experiment was intended only to do that sort of science. It was because those different areas of astronomy stretch the technical system in different ways. So if you build a system that can study the solar system, study supernovae, study dark energy, study dark matter, study stars and galaxies, all the in-between things should come. So it's been 25 years in development, planning, construction. And in June of 2025, there was the big first images released to the world. These were the first images with the full camera, that 10 square degree field of view, that 45 full moons. And it was a huge success. One comparison for success within the project was how many impressions or articles or social media responses were there compared to the JWST big launch that was live streamed and that Biden and Kamala Harris participated in. There was a factor of, I think, 4 or 5 more impressions for this big release, and 5 pages of the New York Times Science Times the week of that first look were dedicated to the Rubin first look images, which was really exciting. So diving in a bit deeper to this technical marvel and what it means in reality for scientists as we're entering these new era. And again, there's been thousands of scientists around the globe in self-organized science collaborations in many different science topical areas, preparing for this deluge of data for well more than a decade. I started way back in 2008 preparing for this, and I've changed what hat I've been wearing in the ecosystem over the last nearly 20 years now. So the movie of the sky aspect is such that within minutes of every image being taken, every 40 seconds, every night for 10 years, alerts will be distributed around the world to anybody. There is no proprietary aspect of these data alerts, so that there will be up to 10 million alerts from every night for where the sky changes and how, with packets of data sent out with enough information for externally provided software, community brokers, to help scientists program filters to find those needles in the haystack. In addition to those very rapid turnaround data, there'll be annual static data sets where images will be taken in different filters repeatedly over time. They'll be added together so you can see an increasingly deep and detailed view of the universe over time. And catalogs will be served out through the Rubin Science platform along the lines of, right, we heard about Sciserver, you all are familiar with that, bringing your software to where the data are versus the way we used to do it back in the old days when I was in graduate school. So, being at JHU, it's appropriate to refer back to, again, the Sloan Digital Sky Survey, which we've heard referred to a few times today. And was it you, Alex? I think that, yes, you gave the numbers. Really one of the most used astronomical data set of all time. And one thing that Alex didn't emphasize when he presented those really incredible numbers of how many scientists not only have been trained up, or students that have gone on to be professional astronomers, thanks to people like Jordan and others creating the portals for early career scientists to get their hands on discovery. I was so excited I forget where I was going. So in addition to that, the SDSS telescope back in the olden days was just in New Mexico, 2.5 meter aperture. That's pretty small. And the sight quality, it was fine enough. This was not a cutting edge telescope, but it was an innovative and cutting edge set of instrumentation and data management system. It was very community focused, and open access was the name of the game. That is how SDSS, at least for a while, was producing more publications per year than Hubble Space Telescope. And I know there's some people that say, well, but were they as impactful, or who was writing them? Were they as, the number of future scientists trained by these data, bar none. So now I'm going to show you the same picture of sky as it was observed in the commissioning observations of the Virgo cluster by Rubin. And what I'm going to show you is not just a single image, it's the co-added emulated depth. You have enough exposures that it's what you would expect after 10 years of Rubin's LSST. So keep your eye on the screen, be ready for the new image. It looks very different. And something I'll highlight to you here, I didn't highlight in the last slide, there's a lot of astronomical sources in this image. I think maybe 2 or 3 of them are stars. Even the ones that look like dots, right? They're distant galaxies. You see a lot of red dots. So red redshift, those are farther away galaxies. Your eye can already start doing some back of the envelope science just by looking at the colors. The bluer things, star forming, also more nearby. The incredible detail in terms of how these galaxies are interacting is telling you a lot about the current and past history of this system. This is a teeny patch of one of the images that will be taken this is a co-added, a teeny patch of the single image of the sky. And each image will be observed across the 6 filters approximately 1,000 times by survey's end. So roughly every 3 nights, any particular area of the sky will be revisited. So I know folks in this room are in a lot of different fields, even folks not in astronomy fields. A lot of the work you do also relies on like image analysis of different types. We saw that cool project DSI, Deep Image DIS, or DIP, Deep Image, sorry, I won't try to remember that. DIP, thank you. Deal with a lot of image work. So you can take a look and think, well, gosh, how would I write software that would measure the color and brightness of everything in that image? Because the light from every object's kind of touching another object. It's not really a straightforward analysis mechanism. And so from the earliest days of Rubin Observatory's LSST, the need for sophisticated data management pipelines was baked in. The data schema needed to serve a wide range of science questions was baked in, bringing in top-line software engineers who, a lot of them cut their teeth on the Sloan Digital Sky Survey, were brought in to write the code that will measure billions of objects hundreds of times, that will run fast enough to keep up with the deluge of data. And then outside of the project, identifying community brokers. I believe there are 7 or 8 of them that will take in some of this deluge of data. And then with a combination of these algorithm advances and frankly, algorithm advances that are still underway, as we're hearing, right? AI technologies are changing on 6 months timescales, is how from billions of objects, we'll find thousands of 1 in a million examples of things that humans have never seen before. So these incredible data are available for everyone everywhere. I've already mentioned that those prompt alerts, those up to 10 million alerts per night of how the sky has changed, will be available to anyone, anywhere in the world. There's no data rights limitations. They're available within minutes of the shutter closing, 3.2 billion pixels right off the camera, coming down the mountain, going to Santiago, going to Florida, and then going to the different data centers around the world. So in US and Chile, the data releases that are coming out once a year will be available to anyone that wants to address a scientific question with them. And then scientists in 29 countries around the globe, thousands of them, through in-kind contributions to the project, will also have access to these data products. And this hugely open access really positions LSST to potentially democratize science. It's a bleeding edge, leading edge data set. In addition to this, the community-centered design that I've been referring to really makes it so that it's not just, oh, here, anybody can anybody can have food on the menu, or anybody can have food at the buffet. We've curated the buffet with input from hundreds of scientists around the globe for the last 15 years to make sure that it's going to deliver what is needed to answer the broadest range of scientific questions. And so the survey strategy, astronomers call this the cadence. It's not just that you uniformly move your thumb around the sky every night. Well, and a human being isn't deciding where to point the telescope, right? It's some program. Well, what about the image quality? What kind of color should we be observing in now? Or what's the cloud cover? What's the humidity? Have we observed this yet? And there were an analysis framework produced by the project, back in 2010 probably, that allowed scientists to have simulated instantiations of the survey all the way back more than a decade ago and produce metrics for how other science questions could be answered with it. Clear, transparent communication all along, a lot of community engagement by the Rubin team, and trainings, getting them used to the Rubin Science platform, how do you access the data. And there have been joint community and project meetings for 15 years. The community has always been able to see what's going on and how the project is confronting questions. So not only is the community input getting integrated into Rubin Observatory's LSST, it's been an incredible training ground, just like SDSS was an incredible training ground for the future leaders in these sorts of fields. So again, here we are, LSST offering the promise of unlimited impact, not just from deepening understanding of the universe, but really unifying, broadening, and enriching global collaboration of astronomy and STEM. Many projects, many proposals have people from a large number of countries on them. And lessons learned in this, first out of the gate project, frankly, to have this kind of open data available around the globe has the potential to provide lessons for data intensive research in other fields that don't have, restrictions or confidentiality on the data. But right, who will get to fully participate? You can't just take this data and put it on your computer. You can't just go into the Rubin Science platform and magically do all of your analyses. How do you know how to write a code that will operate at scale? And even so, I'm sure many people in this room, y'all are the experts of the experts, right? We're at Hopkins. You've got brilliant folks being recruited in from all over the world to come participate in IDEAS and in these software engineering centers. And that's fantastic. But there's brilliant people everywhere at many different types of institutions, and their grad students might not be able to write innovative code at the drop of the hat. So LSST Discovery Alliance, right? I'm no longer with a federally funded project. We're a 501c3 nonprofit that works very closely with a federally funded project. And our vision to address this question of how do we seize the opportunity is we aim to have a future where any scientist with a great question for LSST data will have access to the resources needed to answer it. This isn't about like reaching down and necessarily everybody. There's brilliant questions everywhere is at the center of this, and you get the best science and the most innovative science through democratization. So when we think of resources, we think of tools, we think of training, we think of collaborative networks. Given the audience today, I'm going to give you just 2 examples of how we approach tools as resources and sharing access to those to a very broad community. It's going to be software as a service and software as a product. AI, machine learning, things like that. You'll hear about that from Francois after the break. There's other groups, NSF Simons funded centers in AI that are focusing on Rubin and other things. This is just a small snapshot right now what LSST DA is doing right now. This is my favorite, software as a service. In the specific way that we're approaching this, I don't think it's being done this way anywhere else, and I'd be happy to talk about it more at the break. We're accelerating science through software engineers. Okay, that concept, we've been talking about it all day. We have curating small, very hands-on engagements that have consultation, exploration, and a definition of project, followed by a closely managed engineering effort. And there are several groups of stakeholders. Discovery Alliance were really the administrators. I've got professional software engineers, several of them on contract. These are either people who, they've been working in Amazon and Google and Microsoft, and they've had a great time, and maybe they don't need to really work right now, and they want to contribute something amazing to the world, and they are so excited. They are so excited if they get to consult 5 to 10 hours a week and help scientists make something out of this data set, right? We've got some astronomers turned software engineers, our solution architects. They speak both languages. And they go around and they talk to the astronomers and they say, what are you talking about? I don't need this. Show me your GitHub. Show me your code. What are you doing? What about this? And then they say, well, this is something that we could do to help accelerate your science, and then find an engineer that can help them out. Project Dovetail does not do science directly. These contracted engineers help astronomers do science directly. And so, we go around, we advertise this, and they're like, well, what do you mean? What can you do? This is just sort of table stakes, this list here. These are all a lot of these are bland, boring things. It's nothing revolutionary. But you know what? To a PI with a stable of grad students and a postdoc who's trying to write code and get ready to run it on LSST, or has been building up different analysis software over their 25-year career and are like, how do I get over the hump? Am I really going to make a grad student spend a year on this? Is really helpful and revolutionary. And so, this quote here is from a graduate student at City University of New York. We've run small engagements so far with everyone from undergraduate-focused institutions to R1 institutions like Columbia University and to University of Toronto. And everybody's been super excited and happy. We've also started to work directly for the Rubin data management team. They have amazing software engineers. If anyone in here knows who Frosty is, Frosty only needs to have one name to know who she is, the Science Quality and Reliability Engineering team in Tucson. We've done something for her team because when you have consultants, you don't need to think, I need to hire a full stack engineer. You can bring in people that have some specific expertise that they can maybe do something in 3 or 4 hours that somebody who doesn't have that experience would think would take a couple of weeks to take care of. I'm not going to read this FAQ, but my managing director for this put this together because he's used to getting a lot of skeptical questions from people. They're like, I don't understand it. And so people say, well, how do you give out these resources? What's the proposal look like? There's no proposal right now. You say, hey, I want to talk to an engineer about it. We've done this work so far with just a few tens of thousands of seed funding, so we're really limited and working on fundraising in order to test this model more completely, because we really want to open up doors where small amounts of funding injected can hugely multiply science impact. This is a good one. I don't believe you. They do exist. Right now I have somebody volunteering his time. Again, he just came from leading a team at one of the big software companies, a team of engineers delivering AI products for Fortune 50 companies. And he's like, I don't feel satisfied at the end of the day. But he's awesome, and he's doing some pro bono work for us because he believes in this model. My last example before I wrap up is something funded by Schmidt Sciences. There's software as a product, so not software as expertise, but making large, running at scale software products that are shared use by a number of scientists in the community. And this is called Link Frameworks. And this, much like the Rubin project itself, is a very community-centered design project. The engineering leads are Carnegie Mellon University and University of Washington, Andy Connolly, Rachel Mandelbaum, Jeremy Kubica at those places. Jeremy is the engineering director. He came from Google. And there was a workshop at Flatiron Center for Computational Astrophysics a few years ago to bring in, again, people who are experts in a wide range of science fields related to Rubin to advise, to scope out what would be the most impactful running at scale data products that we could deliver for you. So what's been the impact to date? Over half of the early science papers from Rubin's Data Preview 1 leveraged this frameworks team's work on this large-scale database. Now, DP1, that volume of data is teeny tiny compared to what's going to come out subsequently, but nevertheless, still significantly depended on this frameworks data, including the discovery of the third known interstellar object, just 10 hours of data. Interstellar objects are basically rocks that come from other solar systems. A lot of what we know about solar system formation and contents, we know through the lens of what we see in our own solar system. So having actual examples from other solar systems come to where we are is incredibly, it's a treasure. There was a Schmidt Sciences review of this project, and we've been running software incubators. Our role has been the community incubators, taking some of the best practices from industry, right, and bringing them closer to academia. And so connecting some of the software engineers hired by Link Frameworks with scientists who have needs very well aligned to the framework engineers' expertise and experience, and unanimous 5 out of 5 satisfaction. Very successful. The clients are happy. And just one small example, PI at Queen's University in Belfast, the chair of the Solar System Science Collaboration, is PI of an asteroid simulation package, was sped up by a factor of 150, taking the need to run one simulation of the solar system from 500,000 to just a few thousand core hours. And so to wrap up, right, the time is now. The full camera data is going to come out in 2026. The first full year static data release will come out in 2027. The alerts that I mentioned, those what are all the changes per night, are going to start later this year or the very beginning of 2026. This adventure is just beginning. And I hope I've made at least some of you feel as excited as I am for the opportunities, because they really are truly staggering what this opportunity space looks like, right? I get to interact with folks that have been, again, on the leading edge of software engineering and AI and the work that they're doing, as well as interacting with individuals at community colleges and seeing their students get inspired to go pursue technical careers as a result of some of this. And right, the new software and data technologies for maximizing discovery space are becoming available, and they're evolving really quickly. And a lot of hard work and intentional design are needed to make these widely accessible. Again, in this time of changing culture and data democratization, we could find ourselves in an area where the haves and the have-nots separate at an accelerating pace as the development of data technologies and data science technologies develop at an accelerating pace. And what we do now will have a deep impact on not just LSST, but potentially on other data-intensive projects for the future. Thank you so much for giving me the chance to tell you something I'm excited about.
We're running a little bit behind, but we do have time for a question or two if anyone would like to ask one.
Where's your data processing actually happening? Because this 20 terabytes a night is how many petabytes a year or whatever. So if you've got local compute, which these people from, I don't know, some southern country can access and use to actually do their analysis if they've got this fantastic idea.
Yeah, so the primary processing is taking place at Ssec. There's a US data facility there that's Department of Energy funded, and is also taking place at IN2P3 in France and at a UK data facility in the UK. There is a data center on site in Chile, but that will largely be a storage site and not a data processing site.
Yeah, but I mean, if I've got a brilliant idea about I want to analyze a data set for this particular weird
Yes.
thing, where can that analysis happen? Because I can't download all your data.
Correct. So the answer to that today is through the Rubin Science RSP, Rubin Science Platform. You go on there, you can run analyses that runs either at the US data facility at Ssec or in the Google Cloud on that platform. The community is continuing to realize that there's going to be a lot more compute resources needed that will allow more of the collaborative work that we heard about Gerard, from Gerard, for example. And so I think the answer to the question is going to mature a lot over the next 3 or 4 years. Thank you.
So continuing on that question also, I think the independent data access centers probably will also play into that, right?
Yes, thank you, Ani. And Hopkins is aiming to have its own independent data access center. So the idea of an independent data access center originally came up several years ago when the NSF and DOE were trying to think about what are ways that other countries can contribute to this project in a meaningful way by adding resources available for science. And so there's a number of independent data access centers that are being stood up to provide more resources for funding. At the present time, I just came last month from Poland, where this was a topic of substantial conversation. Not ready for prime time yet. And I am optimistic that they will play a meaningful role, although there'll be a wide range of impacts across the different IDECs. And I would love to see Hopkins throw its hat into the IDEC game.
So I had another question. So that software as a service slide that you showed, and then there was a list of questions. And I was going to ask, who pays for this? And I think you sort of answered it saying that you're still developing the funding model for that, or?
Yeah, so because we haven't been successful in procuring philanthropic investment in this, I'll just be straight up. I've used $50,000 of directors' discretionary funds in the Discovery Alliance because I believe that this is the highest priority program for us to start testing out and showing that it works. We're about to have our first fee for service because the vision that we all have is being able to offer this service in a way that is relatively self-sustaining. And even though the fee for service will still have a fee, and I'm not sure how you do it here, we heard from Edward's talk, it would be at a quite low fee where our contractors are agreeing to accept an hourly rate that is frankly far below their market value in order for us to be able to offer this in a low cost way.
Anybody else want to ask another question while we're still here? Yeah, come on.
Yeah, this again, I think this is great to see all this. But one thing about the democratization, I just wanted to get the perspective on the astronomy aspect of it. Yes. I think like going with the algorithms, the data, the software, all that people are really excited about. But is there a concern that there are significant astronomical investigations that will be missed because there are just not enough people, enough astronomers to work on it, who are supported to work on it? I mean, is that a concern of the project?
So is that the project, the federally funded project, as they should be, is confident that they will deliver on what they have proposed to deliver? I will take the very last piece of what you asked. Is there concern there aren't enough scientists properly resourced to capture, especially the ephemeral, unique things? Absolutely. That doesn't mean the project will not be a smashing success, but the impact would be multiplied by factors of many if we were able to line up the appropriate resources. And again, we'll hear from Francoise There are AI centers that are starting to focus on this. There's a variety of other sorts of innovative approaches we're looking at. And the US federal funding situation for grants for PIs is what it is right now.
Thanks, Beth. That was really great to see all together and interesting. I'm really intrigued by the alert service. When you have so much data, I've followed it from afar because it uses streaming technology that I'm familiar with, and I know the schemas are Avro. What I'm really kind of curious about is the community. Like, if you don't alert on what people need alerting on, they just can't keep up, right? So it's really a critical flow. But I have to imagine a community this large will have widely varying needs and views on that. And so I wonder how you wrangle that. I know the schemas have already evolved like 9 different versions.
Yes. Right? So I'll answer your question in a couple of ways. So my understanding is that the community brokers themselves are relatively, they don't do a lot of filtering. Different brokers may be more appropriate for different science cases. The time domain is not my area of expertise. And that the scientists would bring their own filters to the table. And the community brokers that were identified to get the full flood of the alerts were ones that had the technical capacity to really keep up with it. I think from my perspective, one of the most interesting questions is, how do astronomers have the resources to, develop, train, test, and iterate on those filters? And then what do we do about the fact that, like, follow-up resources are saturated already? Like, the 2.5 meter Sloan Digital Sky Survey was saturating follow-up resources. And to some extent, it's a cultural question. How does the time domain community agree on, like, what's the currency? How do people get rewarded? I mean, there's some really interesting studies of, for example, like gravitational wave follow-up with LIGO, of if the community had coordinated, you would have fully imaged all of the potential area of the optical counterpart. But you didn't, because everybody went for the highest probability area. So, one thing that we're doing, we have some social scientists on the team, and I think bringing in, economists and social scientists as a general practice may be of increasing help to confront some of the more sociological questions associated with how to deal with choices in the limit of limited follow-up. I don't know if that answers, David. Okay. Thank you so much, everybody. I'm sorry I took a little too long.
No, not you at all. Just keeping it tight. Thank you, yeah. Really exciting talk with some super cool through lines to the SDSS. Like, Alex has left the room, so I don't feel self-conscious about saying that like I would otherwise. But thank you so much for keeping us in-house. Like, wow. Okay, hang on. We're going to do another one. So I think we're returning to our seed funding grants now, if I'm not mistaken. Yes. So our next speaker is going to be George Liu. Dr. Liu is a second-year fellow in neurology and skull-base surgery at Johns Hopkins University. Your research focuses on developing precision approaches to treating hearing and balance disorders through the translational application of artificial intelligence and computer vision methods to clinical data sets. As a surgeon scientist, he combines his clinical experience, which serves as a direct source of research questions, with his technical expertise in applied computation and machine learning. He collaborates with scientists, clinicians, and engineers at the Johns Hopkins School of Medicine and Whiting School of Engineering. Prior to coming to Johns Hopkins, he completed his undergraduate degree in physics at Princeton University and medical school and otolaryngology, head and neck surgery residency at Stanford University. So let's all welcome Dr. Liu. Thank you so much for your time.
Great. Thank you so much for the opportunity to present this afternoon. Sure, I'll try that. Well, it's so fascinating to hear about all the other different applications of research with large data sets. I'll be shifting gears a little bit to more clinical and surgical focused project. Our team listed here with principal investigator Francis Creighton, myself as a co-investigator, and Dr. Jenny Chen and Matthias Umbrath. We've been working with the support of the IDIES grant over the past 6 months on this project using artificial intelligence to aid our assessment of surgical videos to perform video-based assessment. I have no financial disclosures. So as an outline for my talk, I'll first discuss the rationale for creating objective surgical skills assessment instruments. Then I'll discuss some prior work leading up to this project, updates on our project, including with instrument tracking, correlating instrument movements with surgical skill ratings, and ending with future work for this project. So to set the stage, there are several modern hurdles to surgical training. There has been erosion of operative autonomy for residents or trainees in surgery. This figure from a study shows that the proportion of resident primary surgeries performed at the VA healthcare system has declined from 15% in 2004 to 5% over a decade later, with resident primary surgeries being defined as cases where the trainee or the resident is scrubbed in doing this case with an attending observing but not scrubbed in. And during the same time period, you can see that the proportion of attending primary cases, which are shown in the dark brown, has increased over that same time period. And this is because of several factors in the healthcare system. For one, the economics of operating room efficiency, or OR efficiency, has not necessarily been favorable for surgical education. These two studies report data that are shown in this table here, showing that when you have a resident trainee in the operating room with a surgery case, you can add 8 to 60 minutes to these example 5 common surgical procedures. And at a rate of $46 per minute in the operating room, that can add up to hundreds of thousands of dollars in terms of opportunity cost with that added extra operating room time. Additionally, there's a chilling effect of the medical legal climate. By age 45, 80% of physicians will have faced a litigation claim, according to one study. And finally, with new treatments, fortunately, there are less invasive approaches to treat different diseases. In my field of neurotology and lateral skull-base surgery, we commonly see patients with benign tumors that grow along the balance and hearing nerves called vestibular schwannomas. And while in the past, a couple of decades ago, almost all these patients would have had surgery, now a large proportion of them will have radiosurgery with radiation or observation, resulting in a decline in surgical cases for vestibular schwannomas shown by these black squares compared to the overall stable prevalence of this disease shown as the triangles. I'd like to turn our attention now to looking at one specific surgical procedure called mastoidectomy. This is a common but challenging surgery of the ear performed in my specialty of otolaryngology head and neck surgery. It involves using a high-speed drill behind the ear to remove the mastoid bone to access deeper ear structures. And part of the reason it is challenging is not only because of the intricate anatomy of the ear, but also because of the fact that it involves using a high-speed drill within millimeters of critical structures like the brain, the facial nerve, and inner ear structures, which if damaged could result in permanent hearing loss or balance dysfunction for the patient. These surgeries are routinely performed with microscopes to allow high magnification view of these critical structures. And the use of the microscopes and endoscopes for other procedures has allowed the acquisition of large video data sets of surgical procedures, which are being routinely recorded each day that surgeries are being performed. And so there arises the question of how can we leverage these large surgical video data sets for clinical applications? And in this talk, I'll be focusing on one particular application for enhancing surgical training. Our current paradigm for surgical evaluation and training is shown in this slide. When a resident trainee is operating with a microscope in the case of mastoidectomy procedures, a video of the procedure is being watched in real time by the experienced surgical attending. The attending then formulates an evaluation and provides feedback to the trainee based on what they observe. And this feedback and skills rating is inherently subjective and is prone, therefore, to implicit bias and is difficult to scale across multiple surgical trainees. One could imagine a paradigm where using computation and modern AI-driven processes, mastoidectomy videos and other surgical videos could be assessed through more automated approaches that would be potentially more objective, less prone to implicit bias, and more scalable. Towards this end, prior to receiving the IDIES grant, our team had conducted prior work along this subject. So video analysis requires accurate tracking of instruments. And just to take a step back, Previous approaches to this challenge has involved manual tracking, which although accurate is slow and labor intensive. The use of commercial motion tracking software, which although fast and automated, tends to be error prone. And so we hypothesized that fine-tuning off-the-shelf AI models could automate tracking of otologic instruments with high accuracy and speed. To do this, we took 13 half-hour cadaveric mastoidectomy videos and used those to fine-tune a state-of-the-art convolutional neural network model called YOLO V8. And this model was able to track the surgical drill accurately in this previously unseen live mastoidectomy surgical video, where you can see the bounding box around the drill head in each frame. And what this type of analysis allows is assessment of kinematics of surgical instrument motion, such as the drill speed and the distribution of drill speeds across the duration of the surgical procedure. And in preliminary analysis, this suggests that there may be some differences in average drill speed between an experienced attending and a training resident, as well as differences in the duration of high continuous drill speed usage, suggesting that kinematic assessments of surgical instrument movements may be helpful for assessing surgical skill. One of the limitations of this prior work was the fact that the instruments in the surgical videos were not always accurately tracked by the model. In these two frames, you can see that the two instruments, the suction irrigator on the left and the drill on the right, were accurately tracked. But there are examples in the same surgical video where the suction irrigator instrument is not accurately tracked, or where neither instrument was correctly tracked. And so one of the first goals of our project was to improve on our automated computer vision models for tracking the surgical instruments. To do this, we've developed a single-shot framework for segmenting the surgical instruments using manual annotations of the first frame only of the surgical video. So in this example, you can see on the left-hand side still frames where in the top left, the surgical drill has been manually annotated with green dots, and red dots are annotations outside the drill instrument. And the bottom left image are annotations of the suction instrument. And what we get, as shown on the right side, are segmentation masks that are shown as green overlays on those respective instruments. And just from the annotation of the first frame of the surgical video, we can get accurate tracking of the surgical instruments in the rest of the video. As you can see in this video, the green shows the surgical drill and the red shows the suction instrument. And what is really exciting about this approach is that not only the accuracy of the segmentations, but also the fact that it can be readily applied to other different types of surgical procedures without requiring a large label data set of previously annotated surgical videos. We're now using this approach to extract the tip coordinates of the surgical instruments, here shown by bounding boxes around the drill tip and the suction head. And this is an area that we're continuing to work on improving. The second update that I want to provide for a project is with correlating these measurements of instrument movements with skills assessment scores. To do this, we use a framework called the OSATs, or Objective Structured Assessments of Technical Skills. There has been an OSAT that's been validated before for mastoidectomy procedures. It involves a task-based checklist shown in this table that are 5-point scores for specific steps of the mastoidectomy procedure, as well as global rating scales shown in this table that describe more holistic assessments of surgical techniques, such as the use of the microscope, use of the otologic drill, efficiency of movement, etc. And what we've done is we've condensed this mastoidectomy OSAT into a more focused 5-question rubric, each question having 5 points to assess 5 aspects of surgical instrument usage that can be applied to any phase of the mastoidectomy procedure. And what we've done is we've taken 2-minute segments of 2 specific steps of the mastoidectomy procedure to analyze. What we see is that for 15 resident performed mastoidectomy videos, there's an overall positive correlation between these focused OSATs ratings with the experience level of the resident trainee. In this case, the resident trainee experience level is shown on the x-axis as a PGY year, or postgraduate year, which is the number of years of training they've had in a surgical residency program. Next, what we wanted to do is look at how some surgical instrument kinematics correlated with surgical skill. To do this, we focused on one specific metric of surgical instrument motion, which is the proportion of time that the drill is on or running. These are still frames that show examples of when the drill is on, shown on the left, or when it is off, shown on the right. And by looking at the proportion that the drill is on, we see that there is a weak but positive correlation of the drill on time with overall skill scores for each of these 5 points on the focused mastoidectomy OSATs. We also see a correlation with the PGY, or the experience level of the resident trainee. What I want to focus on is specifically the correlation of drill on time percentage with overall performance skill score. So one thing that we see in our preliminary analysis is that a low percentage of the drill on time, less than 50%, appears to correlate with lack of practice readiness, which is so this is a red dashed line showing the 50% cutoff line. And practice readiness is the criteria for a skill score of 4 for overall performance. And so you can see that in this example, all 3 videos that had a drill activity less than 50% had a skill score less than 4 for overall performance. And just to see what some of these videos look like, this is one example of a resident performed mastoidectomy procedure that had a low drill on time percentage of less than 25% and had a low skill score of 1. And what you can see is that there is a lot of hesitation, there are a lot of pauses. This may be partly because there is dried blood filling one of the mastoid air cells. And you can see that the resident trainee will stop drilling, will use their suction to sort of probe, and you can almost see the trainee sort of thinking about what the next step is. And this aspect of this hesitation is captured by the low percentage of the time that the drill is on. This is another video where the drill activity time is less than 50%. And in this case, the anatomy is completely normal, but you can see still that the resident trainee has paused, stopped. There are periods where there is no forward progress being made. At the same time, a high drill on time percentage does not necessarily equate with practice ready performance. This is a surgical video that was graded as a 3, so below practice ready performance, but had a nearly 100% drill on time percentage. And what we see in this case is that although the drill is always on and touching bone, the drill undergoes the same repetitive motion throughout the entire 2-minute video with fairly slow progress being made, possibly because there is only gentle pressure being applied to the drill to remove the bone. We also see that there are differences in the drill on time percentage, or the drill activity, between different steps of the surgical procedure. So this is a resident trainee who is performing one of the early steps of the mastoidectomy procedure with the removal of a wide area of bone to enter the largest area cell of the mastoid, which is called the mastoid antrum. You can see that the drill is on for a considerable percentage of the time, greater than 80%. Now, this is a video of the same surgical resident now moving on to a later step where the drill is being used to expose one of the bones of hearing called the incus. And in this part, the drilling is confined to a tighter corridor where there are closer important structures that could be injured, and so care has to be taken to not move the drill erroneously. And you can see that the drill activity percentage of percent on time now is lower at 62%, even though it's the same surgeon. So next, we are working on automating our process for identifying when the drill is on versus off to automate this analysis for future surgical videos. And in our validation testing on previously unseen videos, we're seeing greater than 90% accuracy for classification of the drill state. this is a time plot showing that data as well. And we see this across multiple previously unseen validation videos. In terms of next steps for our project, we're continuing to work on improving our automation of instrument tip tracking, going from our single shot segmentations of the surgical instruments to tip tracking of the suction and drill tips. We were also in the process of obtaining expert performed mastoidectomy videos that would have a skill score of 5 to broaden the range of skills sets seen in the videos that we're analyzing. We're further working on performing assessing multivariable predictors of surgical skill. So not only looking at the drill state of being on and off, but also factors like continuous high drill speed, non-repetitive movements of the surgical drill, and coordination of instruments between the suction and the drill. In the long term, our goal is to eventually develop an AI-aided skills model that can create an objective metric report card to give a surgical trainee after their surgical case, where their surgical video is downloaded, analyzed by a computational method, and then the resident can see what % of the time the drill is on, how they're using the drill in objective measures compared to experienced surgeons. And our goal would be to do a clinical validation study to assess how this type of feedback can improve the rate of surgical skill acquisition by resident trainees. So with that, I'd like to thank you all for your attention. I'd like to thank my team members shown here, Dr. Creighton, Dr. Chen, Dr. Umbrath, our collaborators, students, and funding agencies. Thank you all for your attention. I'm happy to take any questions.
All right, sure, Eric. I think we're going to hold it to just 1 or 2 this time.
Hi, I'm wondering, is it possible to train some like foundation model, then fine tunings for different surgery? Question 2 is like, what's the size of data set we are looking at? Like how long the video you need to train the model?
Are you referring to the single shot framework for segmenting?
Yes.
Yeah, so that framework is built on the SAM2 foundation model for computer vision by Meta, and in our application it only requires minimal labeling. So yeah, so that example, that video of the green and the red instruments being tracked, that was generated from just those point annotations on one frame of the video, if that makes sense.
All right, I think we'll say thank you again to Dr. Liu for another really interesting talk. All right, and we're getting set up here. Okay, so if I remember correctly, there's some pretty domain-specific terminology in this introduction copy, so thank you everybody for your understanding. Our next speaker that I'm excited to introduce is Megan Gellement. Megan is a PhD candidate in biomedical engineering at the Johns Hopkins University School of Medicine. She received her MS in computer science from Tufts University in 2023 and her BS in biology from the University of Alabama in 2016. In the interim, she worked in the healthcare and publishing industries. Her current research focuses on the computational deconvolution of polyclonal Plasmodium falciparum infections. All right. I'm going to say that was okay, with an aim to distinguish recrudescent from new recurrent infections using longitudinal genomic parasite data. Her thesis advisor is Dr. Joel Bader, professor of biomedical engineering and director of the Institute for Computational Medicine, and she is additionally advised on malaria genomics projects by Dr. Matthew Ippolito, associate professor of medicine and director of clinical epidemiology for the Southern and Central Africa International Centers of Excellence for Malaria Research. So, thank you very much, and welcome to Megan. Thanks.
All right, thank you. All right, hi everyone. My name is Megan Gellement, and I'm going to be talking about a project that I've been working on recently in collaboration with my advisors, Dr. Joel Bader and Dr. Matthew Ippolito. And what I'm going to be talking about today is this idea of solving the phasing problem of infection complexity in polygenomic malaria with an emphasis on classifying recurrent malaria infections. So first I want to give a little bit of background on the public health threat that malaria poses worldwide. So in 2023, there were 263 million malaria cases in 83 malaria endemic countries. And these contributed to almost 600,000 deaths worldwide. So Africa is the most heavily burdened continent when it comes to malaria infections. It represents 94% of all malaria cases and 95% of worldwide malaria deaths, 76% of which belong to children under 5. The disease malaria is caused by the parasite Plasmodium. Specifically, the most common of which in humans is Plasmodium falciparum, abbreviated PF on the map here, where it shows the prevalence of falciparum malaria concentrated there in Central Africa. I want to spend a brief amount of time on the current methods by which we treat malaria infections. So the current sort of first-line treatment got its start a long time ago, actually, around the year 340 in China. The Artemisia annua plant was first used in or recorded being used in treating malaria symptoms in patients. It took a while for us to understand how this disease actually comes about, so it wasn't until the late 1800s that Plasmodium parasites were discovered in blood samples of malaria patients, and that mosquitoes were identified as the vectors that bring Plasmodium to malaria patients. So since then, there were several different treatments for malaria, sort of rose and fell in popularity. One you may have heard of, chloroquine, started in the 1930s, is not used so much as first-line treatment anymore due to drug resistance in the parasite. So several treatments that we sort of cycled through. The reason that they're no longer first-line treatments is due to drug resistance. In the 1970s, artemisinin was sort of rediscovered from the annua plant. It was actually the work all the way in 340 being rediscovered and read again that led to artemisinin being extracted and used in clinical trials in the 70s. And by the early 2000s, the World Health Organization updated its guidelines to recommend artemisinin-based combination therapy as first-line treatment for malaria. So it didn't take very long for partial artemisinin resistance to emerge, starting in Western Cambodia. And so sort of concerns about drug resistance to ACT-based therapies has just only grown since then. So one of the primary concerns then for clinicians is identifying, if you have a case where you have a recurrent infection, is identifying whether or not that infection came as a result of treatment failure or from a new reinfection, which is actually fairly common in high transmission areas. So we call an infection recrudescent if it comes from treatment failure, that the drug failed to fully clear the infection. And the patient came back to the clinic and has been diagnosed with malaria again. In a reinfection case, you just happen to live, unfortunately, in a high transmission area where a lot of mosquitoes are carrying Plasmodium parasite, and you've been bitten and reinfected with a genetically distinct infection. And so this is sort of at the heart of the problem that we are trying to solve, is can we classify based on the unique sort of genomic signature between infections, whether or not we're looking at a recrudescent infection or a reinfection. And before I get into those details, I want to give you a brief, high-level overview of what it is that we are even sequencing, genotyping, analyzing. So malaria infection starts when the host is bitten by a mosquito. The mosquito injects these sporozoites into the host, which move to the liver. At that point, they mature to another phase of the Plasmodium life cycle called chysons. They're able to release yet another phase of the malaria life cycle, the merozoites into the red blood cells. And these sort of merozoites, these represent just clones, asexual clones of the same genome, same Plasmodium genome in the blood. And it's from blood samples that we take our samples that we sequence and analyze. There is an entirely separate second life cycle. So some of these merozoites in the blood, they mature into gametocytes that are re-ingested by more mosquitoes, and the parasite undergoes sexual replication in the mosquito, which allows it to develop even more, mutations, drug resistance, and all of that because of this complex sort of two-stage life cycle. So the Plasmodium falciparum genome was first fully sequenced in 2002 by a number of folks many of which currently work here at Hopkins. The genome has 14 chromosomes. It's got about 23.3 megabases worth of data, and it's fairly compact of 5,600 genes. Almost 5,300 of them are protein coding. Another important thing to note about this genome, it is highly repetitive and highly AT rich. So this represents about 80% of the genome and even higher in the non-coding regions. So this poses a significant challenge to genome assembly and analysis. But first we have to contend with one more problem with malaria sequencing, and that is the phasing problem. So one mosquito could be infected with more than one clone of falciparum. You could get bitten by more than one mosquito, each of which is carrying its own unique clone or a set of clones. And now you have a polyclonal infection. And these, again, like in high transmission areas, these are more and more common. So even if we were able to perfectly sequence the Plasmodium genome from your dried blood spots samples, even if we were able to match all of the alleles to the correct chromosomes, actually parsing out which clone this data came from is still a non-trivial problem. And that is what we are attempting to make progress towards solving. So now I want to talk about specifically the type of data that we're focusing on for this project. So we wanted to use a data type that's going to be as clinically relevant as possible. When we think about genomic sequencing, we often think about whole genome sequencing, which is a really great concept in theory, but in practice, and particularly for Plasmodium, it is easier to use panels like these, like molecular inversion probes or MINTs. And what these are these panels of hundreds to thousands of probes that have a specific target region. And what you see here at the top of this figure is the probe hybridizing to the with two arms that are complementary to regions that flank your target. And then you see further the amplification steps that happen down the line to produce the sequence that we ultimately sequence using the Lambda or whatnot. So the target sequence is around 100 base pairs, and it captures up to thousands of SNPs. And although we don't get the entire genome, we do get a product that we don't have to map to a reference. And so it takes away some of that ambiguity, even though there's a little bit less data to be had. So ultimately, what we would love to be able to do is take a MIP panel from an individual and generate the full genotype, or not an entire genotype, but so much as can be generated from a MIP panel of each clone in that patient. And I won't go through every panel of this little figure, summary figure here, but the basic idea is that we curate training genomes, and from that we are able to synthesize training data where we can generate known sort of ground truth for mixed infections, train and validate a model in order to phase data, and then that phase data can be used to classify infections as recrudescent or new. So the data set that we are working with right now it's longitudinal MIP data from 13 patients who were part of a larger therapeutic efficacy study, or TES. The study was conducted in Zambia between 2014 and 2015. And one of the interesting things about this data set is that we have 2 patients from that data set who went untreated and have off protocol between their first and second sample, which means we have an approximation of what a recrudescent infection could potentially look like in the field. So the blue bars are this follow-up period during which patients were checked in on, and any of the yellow bars within there, that represents a positive blood smear where they were diagnosed with malaria. So for patients 22 and 60 with little stars, between the first and the second sample identified there was no treatment. And so we know that those are the same infection, or at least contain elements of the same infection. So the way we measure the polygenomicity of infection, or complexity of infection, as it's called, one of the means of doing this is you deep sequence a specific gene, a specific high diversity gene that is conserved. It's important to the Falciparum genome, so we know it's conserved across clones, but there's also a lot of diversity in it. So when you can measure that diversity and set a sort of a threshold for how much of this, allele do I see before I'm going to call this a true indicator of a new clone. And you can use that kind of measure complexity of infection in your data sets. And so we also have this AMA1 deep sequencing data for the same 13 patients. And that gives us a complexity of infection anywhere between 1 and 16 different clones per sample. So this is a new data set, data type to us, and one of the first things we have been working on so far and making good progress through is just the data cleaning step. So there's an artifact of the MIP technology that leaves these sort of ragged ends or spurious bases left over on the ends of reads, and these are often characterized by just single nucleotides or repetitive poly sequences. And this can lead to incorrect allele classification, because if you are using shared alleles between these longitudinal samples to try and estimate whether or not we're looking at a recrudescent infection, and we are seeing a whole bunch of alleles that look different, you're more likely to get a false negative for recrudescence if these artifacts are present in the data. So we have been working on methods for determining how to remove these spurious ends from our data, and we can get progress with that. And the other thing that sort of working through this new data set has given us is a set of sort of parameters or guidelines towards the model that we are developing that we want to focus on. So, and one of those is a model that's robust to missing data. So This image that you see here shows the proportion of total loci captured versus the parasite density on a log scale of parasites per microliter. So that's measured microscopically. And you can see that there is a relationship, right, between the density of parasites in the patient's blood sample and the proportion of MIP loci that where we've been able to recover data. There were 1,783 total loci in the panel, and most of the samples captured most of the loci. But when you have particularly low density, these MIP panels just perform worse in general. So this is an inherent problem to Plasmodium sequencing, to any sequencing method that you might choose to use, because of that variability in parasite density. And this offers opportunities for imputation-based methods development that we'll be focusing on as we build out this model. Another thing that we will be focusing on is development of a model that's robust to allelic association. So when we have two or more alleles that are occurring together more frequently than we might expect by chance, we say that they're in linkage disequilibrium. And so since we're ultimately trying to construct complete chromosomes or genomes, a good first step is to identify these loci that are associated and sort of start grouping them and kind of build that up from there. As sort of a baseline, we established a sort of a maximum likelihood model based on the number of shared and unshared alleles between time points, and without accounting for these things that I mentioned, data missingness or LD, we cannot distinguish between recrudescent infection and new infection. So these are important considerations going forward. And to address that, one of the things that we will be sort of leveraging is public data sets. So MalariaGen is a network of Plasmodium and other parasite data. And their most recent release, PF8, contains over 33,000 genomic E. falciparum data samples. So can we leverage sort of allele associations in this public data set to inform the parameters of the model that we are ultimately developing? Since there is a sort of high stratification in Plasmodium genomes by region, we're going to focus specifically on those samples that originate from Africa. We're going to focus specifically on those samples that are estimated to be monoclonal, so they're not polyclonal infections. So we can sort of tease out more information there that is not confounded by these multiple genomes. And when you separate those samples, we get about 7,700 of those. And from these, we can subset our MIP regions specifically and create sort of a mock MIP data set that mimics the same sort of level of information that we have in our data set. And we can use this information to assess LD and create training data, which is what we are focusing on going forward. And with that, I would like to thank the IDEAS Institute for the opportunity to start working on this project. This is a new project to me that I would not have gotten a chance to get started on without IDEAS. And I would also like to thank, of course, my thesis lab, the Bader lab, my advisor, Dr. Joe Bader, Dr. Matthew Ippolito, and everyone in the Ippolito lab for their expertise on malaria, malaria genomics, as well as the Bailey lab at Brown University for initial analysis of and sort of pre-processing of the data set that we are working with. Thank you so much. Take any questions.
Right to an E for questions for Megan.
So you you said in one of your earlier slides that it is a global problem. It remains a global problem, but are we winning? Like, what's the trend?
I believe that, if I'm remembering correctly, the global incidence rate was down about 5% between 22 and 23. So, maybe. I am not, by any means, a malaria population expert, unfortunately. As I said, this is something that I've sort of just begun studying. But yeah, I think maybe.
Anyone else with questions for Megan? Oh, thank you.
Yeah, so this is about the longitudinal studies, like there were like 13 individuals in that. But are any of the other samples collected part of other groups' longitudinal studies, or is this the unique one that's being done? Or can one pull in more, increase the sample size by just looking at other longitudinal studies as well? And the second part is, how important is it that this is done in the same local region? Or how much would you do it in Zambia, do somewhere else in Africa? Would it confound things, or would it still be you could use all of them?
Sure. So I am not sure the fraction of like the public malaria gen studies that are longitudinal. I don't think that's something that I don't believe most of them are. So that's not it's not really a sortable parameter. So I believe more longitudinal studies will likely come through additional collaborations mostly, and then as far as region and how important region is, depending on how much parameters like linkage to equilibrium matter in sort of the construction of the model, I think the region will be pretty important because, as I said, there's a genetic distance that increases the further apart the populations are. So if malaria infections in India and malaria infections in Africa are not necessarily as related as malaria infections, that are a few hours down the road from one another. So there might be some sort of regional tuning that is helpful.
All right. Yeah, one more question.
Do you think that the database that you're training on, does it have pretty much all the diversity you need? Like, is it rapidly evolving, or do you think you actually have enough information to solve, in that local region?
I think it's a good start, but it has been rapidly growing. So I think it will always be helpful to have more, and the more that we can get like specific to the region where our MIP sample data is, the better.
All right. Thanks once again to Megan. Everybody, round of applause.
So this allows me to do the pleasant thing, which is to introduce Dr. Francois Laos. He is a CNRS researcher. He is an expert in deep learning, but also in statistical modeling and cosmology. And he has been using deep learning approaches with physical modeling to analyze cosmological surveys. He's a guest researcher at the Flatiron Institute in New York City. He has worked at CMU, at Berkeley in different roles, and we're very delighted to have him here to close out today. Thank you.
All right. Thank you so much for the introduction and for the invitation. It's been a great day to hear about a lot more than just astronomy, which is usually what I hear about. And so to close this session, I'm going to try to bridge the gap among the different topics that we've heard today about like compute just right now, but about large-scale availability of data and where AI can start to play a role at this intersection. And so what I'm going to show you today is our efforts in this group that we call Polymathic to try to build scientific foundation models and to deploy those in different areas of science, but like what we're going to talk about today is survey astronomy more specifically. Okay, so to begin this talk, I want to show you a picture of the intake of AI and machine learning in the field of astrophysics over the last few years. So you probably all know that around 2014, 2015, there's been this explosion of methods following CNNs and deep learning in general. And those have slowly, gained a lot of traction in this field. And this picture that you see for astronomy is actually very general. You would find something very similar in other fields. But one thing that is kind of hidden behind this picture is that the vast majority of these results has been based on supervised learning, which means models that are trained for solving just one task and that are almost always trained from scratch. And that limits fundamentally our ability to deploy machine learning in a number of use cases. And so I'm just going to illustrate a few of those instances in the field of astronomy. The first one is in settings where we have very limited availability of supervised training data. And so these cases can be, for instance, when we're looking for very rare or novel objects on the sky. So for instance, in LSST, if we're looking for objects that look like this, those are strong gravitational lenses. We only know about a few thousands of those on the sky. So that would not be enough to train a large-scale deep learning model. The other situation where we're limited to limited training data is when we're doing what's called simulation-based inference, where we run simulations, and then those simulations will be compared using machine learning to data in order to infer physical parameters of your systems. And in these kind of applications, you need to train this network that's going to compare simulations to data, and that can require a large number of simulations, which is also very costly, and so you're, again, in this data-limited regime. And then the second point is that because these networks have been trained from scratch on specific problems, then they're usually never reusable. And so you have a lot of waste of resources that way. And at the end of the day, when you're trying to do analysis of your data, you're going to be faced by these two limits in practice. So that has been what we've been doing in scientific applications domain. But at the same time, in the broader field of computer science, there has been a huge shift in the way that you build deep learning models. And that has been with the rise of this concept of foundation models. So you probably already have heard of those. The idea is that instead of training models specifically for one particular task, we're going to train a very large model on a very large corpus of data, which is not specific. And then once this model has been trained once, we'll be able to specialize it to a large number of tasks. So just to give you an idea of how you would do this for something like images, one way to pre-train those large foundation models is just to train them to solve those proxy tasks, like filling up the gaps in those images, for instance, here. It's not a task that is associated with a particular scientific goal, but in order to do it, this network here will have to build its own representation of the data that will have to be very informative, that is then going to be able to be leveraged for a second phase of adaptation where you can take this encoder and you can use it to solve some downstream tasks. So just to show you an illustration of this strategy on a very classical computer vision task of classifying images, cats and dogs, what you see here on the left is several generations of supervised models, and as a function of time and years, and the size of these bubbles tell you about the size of the model that you're able to train. What you can see is that, yes, we've made progress in terms of accuracy with time. We've discovered better architectures, but But fundamentally, you remain limited in the size of the models you can build because you have to rely on an existing supervised training set, which will fundamentally always be limited in size. And the model that you see here on the right are taking this different approach, where you first train these large models without labels in a completely task and agnostic way, but on much more data, because now you don't require to have, costly annotated data, and then you adapt them to the task at hand. So you can reach much larger model sizes, and you will also get a boost in performance compared to the previous methods. So that's the kind of thing that we like to see in science. And the question that brought our group together a couple of years ago now is whether we can translate what, has emerged in computer vision to our particular scientific applications. So that has been the motivation for our group that we call Polymathic, which is founded by Schmidt Sciences and the Simons Foundation, with a lot of people from a number of different groups. And the entire initiative has been led by Shelley Ho at the Simons Foundation and Flatiron Institute. All right, so why did we need a dedicated effort? So this first plot that I show you is a very short and not complete survey of all the recent progress in language vision models. And the main point is that there is a ton of them. And what this also translates is the progressive integration of different types of data modalities inside same models. So the latest generation of Gemini models, for instance, that you can have in your phone right now, are able to understand jointly text, images, audio, and soon videos. But it won't go much beyond those standard kind of data modalities. And so if we want to transpose this kind of foundation models to our scientific applications, we're faced with a number of new problems. The first one is that scientific data is intrinsically much more complex and diverse than just text and images. And that impacts our ability to create large data sets because you will need to have a lot of expertise to gather a lot of data that you can use. And we'll also be faced with new challenges around the kind of architecture that you can build that will be able to act on this more complex data. And the second point, which for scientists is almost, if not more important than the first, is that we need to have very rigorous way that you can use those foundation models for the task that you want to apply them for. So you're all familiar with the problem of hallucinations with language models. So if I'm trying to solve a scientific task, I do not want to be faced with this sort of issues. Right, so now in the rest of my talk, I'm just going to go through those different challenges and show you the strategies that we use to try to address them. The first one being the data challenge. So the key in our ability to develop those large foundation models have been the availability of very large corpora of training data. So for instance, in the realm of image and text, there is data sets such as Leon 5B that are a collection of 5 billion examples of image and text pairs. And so one thing that can be counterintuitive is that data sets at this scale do not exist as readily as from the internet for scientific data. One of the problems that you're also faced with here is that I'm not just interested in the image itself, I also need to take into account the metadata that comes with an image or with some measurement. And the way to illustrate this is that the images that I show you here are 3 different images of the same patch of the sky, but seen by 3 different instruments. So the details of the image are going to be different. The size of an object is going to be different in that image. So I need to understand where this image comes from if I want to make very simple measurements like what is the size of this galaxy that I see here. I need to take into account the properties of the instrument that acquired it. The second point is that we don't only have images, we have also spectra, we have hyperspectral images, we have time series, we have lots of different types of data and measurements. And the final point here is, for instance, myself, I'm an expert in this kind of data here, so I can tell you where you should download it and how you should use it, but I'm not an expert in those hyperspectral images. And so there is a segmentation of the expertise, even inside a domain like astrophysics, on who knows how to assess data and how to use it for doing something useful with it. And so those are the specific challenges that we had to deal with for building such models here, in particular in astronomy. So the first project that I want to show you is something that we call the multimodal universe, which is the first time that we aggregated hundreds of terabytes of data from multiple instruments, multiple surveys in one consistent fashion that we can use then to train large-scale foundation models. So that's a project that was accepted and presented at NeurIPS last year in the dataset and benchmark track. And essentially, the goal here has been to build this dataset that will span a lot of different use cases that people have for machine learning and astrophysics. So the strategy is, number one, engage a broad community of AI and astro experts. And so that is always going to be crucial, because one of the challenges that I mentioned is this, let's say, segmentation of the expertise across an entire community. So we reached out to about 30 scientists, all with different kind of complementary expertise. We worked with them on acquiring data from a large number of surveys, with a focus on making sure that we were also able to cover a variety of different subfields of astrophysics. So for instance, we have images from a lot of ground-based surveys. We have space-based data from the James Webb Telescope. We have time series. We have hyperspectral data from MANGA and much more. And then the last point has been working with those experts again to try to come up with a set of conventions that we could adopt such that data would be standard, and then that you could train very efficiently large-scale machine learning models on top of this. And one thing that may be, not that obvious, that data in the shape and form that it lives naturally in surveys or in the databases where they're stored are absolutely not compatible with training large-scale models. So you have a lot of work to do in this standardization. And at the end of the day, our strategy kind of looks like this. So we have data that can come from many different sources, and we want to have a way to unify them. So the way that we go about this is that we work with domain experts, with scientists that have expertise in one particular survey, to write a small piece of software that we call a Dharma script, where they can use their own expertise about what is good data from that survey, how do I access the database, how do I download all of that data. And then the output of this script is now going to be in some standardized fashion that we impose. And so just to show you this kind of standardization that we impose is that for something like an image, we're going to say that an image is only going to be able to be represented by a few fields, like the flux, which means how much photons you get per pixel, and some additional metadata that will allow us to understand that image for the downstream processing. And so when we do this for all these different types of data, we can then process jointly all this data, which we did at Flatiron, and create this large database of all a large collection of survey data that we can then also cross-match. And so, for instance, for one particular object on the sky, we can access data that can come from different surveys of that particular object. And that's going to be crucial for what I'm going to show you after. So at the end of the day, we collected in the hundreds of millions of examples, images and spectra and time series. This is not yet the billion example scale, but that billion example scale will come with the next generation survey, such as the Rubin LSST. And just to show you other efforts that we did in the same spirit of collecting data, this is a data set that we call the WELL that we also developed at Polymathic, which is the first time that you have a what we call an ImageNet scale data set for fluid dynamics that is, again, aggregated from a lot of different sources and stored in a standardized way and accessible very easily at this link that you can find here. And again, this is something that's been presented at NeurIPS last year. I'm going to not say too much more about this, but I just want to flag that making data available for AI application is scientific data, I should say, is a trending topic. And just last week, Hugging Face released this Hugging Face science heat map, where Polymathic is number 4, just after Meta and way before NASA, so we're pretty proud of that, on delivering data sets for AI based on scientific data to the community. So feel free to have a look at this. There is also a bunch of very other interesting work by these other groups. Cool. So now that we have this data set for the first time in one standardized format and accessible for GPU training, there is a question: how do we build an architecture that can actually work across these different types of data modalities? So I talked about time series, spectra, images, and such. So here, I'm going to show you the spectrum where on the left, we have very specific neural networks that are going to work really well for one type of data. And on the right, we have the ideal type of network that one model would be able to act on any type of data. So the left is really very much what we had as of a few years ago. So here is a few examples of work, including myself, where we did specialized models that were great at working with spectra, for instance, or very good at working with images. But those, are specific for one type of data modality. And then if we want to dream a little bit, we can imagine what would be on the right of this plot. And my ultimate goal would have to be one model that can work on any type of data that you can throw at it. If you think about it, the most lowest level denominator that you have for any type of data would be the byte level data of the hard drive representation of your data. And so that can sound a little bit futuristic, but people have already shown, for instance, in this paper, that you can build a transformer model that works directly at the byte level. And in that, at that level, it is universal to any kind of data that you can throw at it. So this is still, unfortunately, a little bit, future tech. We're not there yet. And what I'm going to show you is a few generation of attempts that we've made at Polymathic for kind of closing that gap and trying to go towards general architectures. The first work that we released last year that was called AstroClip, which is based on the idea of still having dedicated architectures per data type, but then finding ways of aligning those architectures so that it can create a joint representation between different data types. So I won't have time to tell you too much about this, but this is very similar to some work that has been done in image and language work, where you can build joint representation for image and language. And the work that I want to show you today is much more recent, something that we're just going to be releasing next week, actually, which is based on a deep integration of the different types of data modalities into a joint model. So these kind of models that are broadly referred to as early fusion multimodal models are in contrast to the first attempt that people made at combining, let's say, data in the form of images and language inside joint architectures. So a few years ago, the way that you would build something like ChatGPT that integrates images and language would be by artificially plugging an already trained vision model inside an already trained language model. And so this can work up to some extent, but it will always stay kind of like plug after the fact. And another approach that you can take is first standardizing the different types of data that you have in the sense of getting standard tokens. In the same way that you would tokenize a sentence for a language model, you can tokenize an image, which is turning it into just a sequence of numbers, essentially. And now that every type of data that you have is just a number or a sequence of number, you can train a single model on all the data that you have available. And that model will natively be able to understand the relationship between the different data sets that you would have trained on. And so that's the kind of model that we trained and deployed in astrophysics that we called AON for Omnimodal Astronomical Network. And that has been a significant amount of work for over a year by a pretty large team. And here are some of the people that have led this effort. And that has been just accepted at NeurIPS, so we'll be presenting it in December in San Diego. So what is this about? So the first point, again, when you want to train a foundation model, you need to acquire a lot of data. So our data set here for this model has been based on this multimodal universe that I just mentioned. And it will require, it gathers a few different subsets. So the first subset is image data that comes from this legacy survey collection of data. These are images of galaxies that have a certain number of bands. And that is in the hundreds of millions of examples. We also collected data from a different instrument, HSC, which, although they are still images of galaxies, they have a different number of bands, so a different number of channels, they have different pixel size, and they have different image quality properties. We also went for another modality for spectra. So we collected from the Dsai instrument, which is essentially the future of SDSS, which is currently running, Those will provide high-resolution spectra, not only for galaxies, but also for stars. We also grab all the spectra from SDSS, and we also grab spectra from the Gaia telescope, which has a low-resolution spectrometer that is in space, and this time will only tell you about stars. And we aggregated these data sets because in one data set, we can answer questions about a large number of subfields in astrophysics, from galaxy formation to galaxy archaeology. And so that will allow us to make our point that one single model can be used for a number of different science cases downstream. So the first problem that you have to deal with is, how do I standardize all of these data modalities such that I can then train a single model on top of it? So the strategy here is to build essentially autoencoders that are going to be able to grab any type of input data that you have and represent them in a consistent fashion in a set of tokens. And again, a token is just a number. So I won't have time to go into all the details of how we do this, but we do this for about 39 different modalities. Those modalities can be can be images, spectra, physical parameters, or a bunch of different measurements that the instruments of the pipelines are able to produce for us. And I'll also flash that building these tokenizers or these autoencoders is not very easy. And so we spend a lot of time building models that are going to be universal in the sense that they can tokenize any type of image or any type of spectra. Once we have the data that is tokenized, we can then think about building this universal model, if you want, of all the data from our surveys. So the way that we will train this model is first by finding associations of the same physical object as seen through different surveys. So here, for instance, you can see that we have spectra from Dsai that have counterparts in imaging data from this legacy survey, and all these sort of combinations. So we grab these data sets combinations, we tokenize for one object, all the data that we have available for that object, and then we train one large-scale autoencoder model, transformer encoder decoder model. So these are very similar to similar models that have been made in natural language. And the way that you train them is by randomly selecting tokens from some data modalities and asking it to predict the remaining tokens. And so in doing this task, what you're actually trying to learn here is a joint and all the conditional distributions of all data modalities. So sometimes you will show it like just an image as an input, and you will ask it to predict the spectrum. And most of the time, it will be some combination of input data and asking it to predict some combination of these outputs. The next component is training such model, and this is where we're going to plug back to the question of having a large amount of compute available. Very similarly to training language models, this is not a trivial task. For this extra large model that reaches in the 3 billions of parameters, this will take about 300 GPUs, H100s, for like 3 to 5 days. And we have even a much larger model that goes up to 10 billion parameters that would take 500 GPUs if you want to train it very efficiently. And those curves here are validation losses that you can see for different sizes of the model. The main point is that you can see that this validation loss goes down as you go towards larger scales. Just shows that larger models are better able of capturing the diversity of your data. I'm going to skip about the technical details. If you want to know more about how you do this at a high performance level, feel free to ask me questions afterwards. And I'm just going to flash a few results of out-of-the-box capabilities that you get with these models. And if you remember, they are able to model any joint and conditional distribution. So if we look at this example here on the right, what I'm asking the model is to take a low-resolution spectrum from this space-based instrument, and I'm asking it to predict what a high-resolution spectrum for the same object would look like from the sky. So the low-resolution spectrum would be this red line that you see here, where you cannot see much details. The true spectrum for this object that we can measure from the sky, from the ground, is this black line here. And what the model will predict is this blue line. So it's not perfect, but the point is, even though you cannot see those lines and those features in the low-resolution data, the model is capable of placing them, so super resolving essentially this kind of observations. So this is nice, but this is not exactly the way that we want to use them for doing science. The last piece that I mentioned a few slides ago was that we need a very robust framework such that we can trust the model, we can trust that it's not going to make hallucinations, and we can use it for doing actual science. So the framework, I'm going to skip a few slides here, but the framework that we want to use here is the following, where we're not going to use the generative modeling capabilities of this model, but we're just going to use it as an embedding model. This is not the only way that you could do this, but this is the simplest way. So what we do is that we truncate it here. We only grab this encoder piece here, and that encoder is essentially capable of taking any inputs that you have, so any set of tokens, and turning them into embeddings. And then for a given application that I have in mind, I can train a very simple adaptation layer on top of these embeddings to turn these embeddings into predictions for whatever I'm interested in. The main point is that this adaptation layer can be just a single matrix or just a few matrices if you have an attentive pooling here. So this can be trained very effectively with very few number of examples. And then if that's the case, you can now build a prediction model for any task that you're interested in just a few lines by just saying, oh, here's my new data for whatever problem that I'm interested in. It's data that comes from this instrument. I can tokenize it, and I can build a fine-tuned or adapted version of my foundation model by just showing it a few examples of labels for the task that I'm interested in. And then in a few lines now, you have a state-of-the-art prediction model for whatever you're interested in. So I'm going to skip some of the results. Maybe I'll just show you this one here, where what I'm showing you is on a particular task of classifying types of galaxies, so morphologies of galaxies. What you see here on the plot on the right is if I were to train a supervised model for this, the best kind of supervised model that you have, as a function of the size of my training set, I would fundamentally always be limited in accuracy, and I cannot get above 80% of accuracy here. And getting any of these annotation here means there is some human expert that has spent their own very valuable time looking at this data and putting annotations. But in contrast, if we take this very simple adaptation layer, again, it's just a linear matrix that is plugged onto our pre-trained model, we can adapt our model for this classification task very efficiently with just a few examples, a few thousands of examples. And we can also beat state-of-the-art vision models like DynoV2 from Meta for this kind of task and this kind of scale. So this works really well for galaxies. It works for stars. I won't have time to show you. It works also for dense tasks like segmentation problems. But maybe the most exciting thing for me is the ability to use this kind of pre-trained model also for retrieval. So the embeddings that you get, they have this nice property that you can look for similarity of alignment between embeddings. And so if I have one example, I can take its embedding and I can look for what are the closest examples of a very large data set that will match this example in this embedding space. So here are a few examples. So this is something that is pretty trivial. It's a spiral galaxy. And the example that I can retrieve by the similarity metric are very nicely also spiral galaxies. The one that I show you here at the bottom is something much more rare. Those are gravitational lenses. And those are the 1 in a million that we heard about earlier today as well. If I have one example of such an object, I can retrieve very efficiently other example of those. So here, the 6 most likely or similar example is already a strong gravitational lens. And that has been evaluated in a set of 500,000 of galaxies, of such set like this. So it's very efficient. And the last point that I'll mention is now that we also have this embedding, we can do very cool things, like, for instance, aligning those embeddings to natural language. So we had an intern over the summer that developed this demo here, where he trained a language embedding model, aligning it to our pre-trained embeddings from Aeon, such that now you can query very large data sets with natural language in a way that you could really never have done before. So just a few examples. Here, what you have over here is being able to query, I'm interested in finding a merger of galaxies where I can see multiple arms. This is not something that you can do with a SQL query. This is something that you can express in language. I'm going to skip some of the details here, and I'm going to go towards the conclusion. Why are we so interested in such foundation models as scientists? The number one point is that now that a model has been trained on essentially all the data that you could potentially apply it to, I, as a scientist, never have to waste my PhD students' time on rebuilding such models. They can just grab one off the shelf and it will be state-of-the-art very efficiently. The second point is that now we can do state-of-the-art machine learning, even in those regimes where we only have a few examples. So that can be when we have very rare objects, or where we need to rely on very expensive annotation, which can be complementary observations, or which can be asking human experts to annotate examples. And finally, the fact that we can do these state-of-the-art results with very simple machine learning, I showed you a linear projection matrix, means that as part of the processing of future survey, we can envision just computing those embeddings. It will be just one other entry in a catalog. And then with just scikit-learn, essentially, I can build those very powerful applications directly from the data that is available at the catalog level. I'm going to stop here, and thank you very much for listening.
So what if taking the embeddings from constructive learning, compared with this embedding, training in this way? I mean, in terms of for example, you're defining some similarity scores for retrieval,
Yeah. So I cannot tell you at equivalent number of parameters. We don't have those numbers, but I can show you this is our previous generation model, AstroClip, that you see on this line. And this score is essentially your efficiency at finding the objects you want in the first 10 examples. And so you can see that these models here are generally much better than this contrastive learning model that we have built before. To answer the question.
Yes, so this is fascinating. So I was interested in the metadata that you carry when you're doing this multimodal model. What is the metadata typically that you carry, and how much of it is used, say, in the new thing that's coming out tomorrow, do you use the metadata?
So that's an excellent question. So in this first generation of models, we essentially condense the metadata in what we call a modality embedding. So that means if I have an image that comes from one particular instrument, I will add a vector, if you want, at this input of this transformer that tags this image as coming from this particular instrument. So this is not scalable because it assumes that you have a finite number of combinations. For this first generation, that was fine. In the next generation, what we'll do is have something much more flexible, which can actually ingest the real metadata that comes from the instruments at the example level. So we'll have something about the amount of noise in that image. We'll have something about the size of the blurring of the PSF and such, and then build an embedding from those, and then feed that embedding to this model along with the tokens. You could imagine even more complex methods, depending on use case. Yes, so we are very glad that they are now accepted for publication, and they went through our internal review process, and now we're just about to push them on the archive, and they are going to be available on Hugging Face as well. So you should see that on Twitter next week. Well, that would be a great use case for your bugs. Yeah. Totally. So that's okay. So sorry, maybe I missed that point, but this is the entire point here.
Yeah.
So we started with astrophysics because a few of us were astronomers, and so that's a field we understood, and we knew where we were going to make some mistakes, or we would be able to tell when we're doing something stupid. At the moment, we're working also with people in biology, and the exact same model you can also deploy it on RNA, on DNA, on protein data, because it's all data that you can tokenize. You can tag it with where it comes from and such, and you can learn the relationship between all of these data sets also the same way. you can then achieve the same kind of embedding models. The way it's also really cool is that you can do conditional generation. So I can like have an input sequence, can be DNA or RNA, and I can ask the question, what is the protein going to look like? What's the 3D structure of the protein going to look like? And it's going to be a conditional generation model. So you'll be able to sample several possibilities, which you can then test and check for.
I'm more interested in the imaging applications, actually, as a microscopist. Yeah, shove it a cell type and say, find me all the cell types in this data set.
Yeah, 100%. Yeah. So that would be, I don't want to say simpler, because I know that's always more complicated than one thinks. But this would be a straightforward translation, of this framework. That would be
great. Very interesting. Thank you.
Okay, I think we can just thank our speaker again for a wonderful talk.